This is the sixth video in the series and we're going to look at geometry and measures. Let's start off by looking at rectangles. Here is a drawing of a rectangle. A rectangle is a quadrilateral. That means it has four sides. In each corner of a rectangle we have a right angle. A right angle is shown by a little square. Each of these are now 90 degrees in size. What I'm now going to do is draw a square. A square is a type of rectangle. With a square, each side length is the same, and we can show that by putting a little line on like so. What we're going to do is start off by looking at finding the area and the perimeter of a rectangle. The area is the space inside, and the perimeter is the distance around the outside. The easiest way to find the area and perimeter is counting squares. So if we look here, it says find the area and perimeter of each shape by counting the squares. So on the first one, let's look at the area. We can see that we've got 3 here and 3 here. We've got 2 lots of 3, so we can say now that the area would be 6 units squared. Whenever we've got an area, the units will always be something squared. That might be centimetres, metres, kilometres, or just units squared. So I've got 3 here and 3 here, or 2 lots of 3. If I now consider the perimeter is the distance around the outside. I've got 3 here, I've got 2 here. At this stage, I could simply count 3 and 2, which is 5, and double my answer, because I've got exactly the same just here. I've got 3 here, and I've got 2 here. So we can say the perimeter, which I will call P will be equal to 10 units. Whenever we're given perimeter is a length, so that will simply be the units, whether that's centimetres, metres, kilometres, or just units. It's never squared. So if we look at the area on the next one, we can say now that the area of this one is going to be 3 units squared. And the perimeter 1 and 3, that's 4. I simply double that up. So the perimeter is going to be 8 units or 8 squares. Here is a square. We've got a 2 by 2 square. So the area is going to be 4 square units. And the perimeter, we got 1, 2, 3, 4. We double that up. And we say now that the perimeter is going to be 8 units. So that's the easiest way to find the area and the perimeter of a rectangle. If we're not given squares, we would simply go ahead and look at the dimensions. When we're finding the area of a rectangle, we multiply the length by the width. So the area is the length times the width. You can choose which the length and the width is. We simply have 2 and 3. So in this particular one, we can say here, the area is going to be 2 times by 3. That gives me 6. We've got centimetres, so the units are centimetres squared. If we look now at the perimeter I've got now the 2 and the 3. What I could do is write out that this is going to be 3 plus 2 plus 3 plus 2. A common error when we have this particular example is that students just write down that the perimeter is 3 plus 2. They don't consider the other sides. If I did this, we can see now that that is going to give me 10, and the units we have are just centimetres, certainly not centimetres squared. Alternatively, what I could have done here is said that the perimeter was going to be 2 lots of 3 plus 2 lots of 2. So I've got 2 lots of this one and 2 lots of that one. If we look at this one just here, then the area is going to be 1 times by 5. That's going to give me 5, and the units will be metres squared. The perimeter, we're going to have 2 lots of 1 plus 2 lots of 5. That's going to give me 2 plus 10. So we'll have now 12, and that will be metres. On the last one, we can see this is a square, so we can say the area is going to be 8 squared, or 8 times by 8, 8 times by 8 is going to give me 64, and the units will be millimetres squared. The perimeter is going to be 4 lots of 8. All of those are the same size. 4 lots of 8 is 32, so that will be 32 millimetres. We might be asked to find a missing length. So here it says find the missing side lengths of each shape and each perimeter. So on the first one we have the area. We're given the area and the area is 42. So what we want then is a side length, and let's just say this side length is going to be x. So we know that 7 times by x is 42, so x will be equal to 42 divided by 7. The length times the width is the area, so the area divided by one of the side lengths will give us the other one. So that's going to give me now 6. 42 divided by 7 is 6, so we have 6 centimetres. So all we're going to do is write that this is 6 centimetres. So the perimeter, we've got 6 plus 7, which is 13. We can double that up and say that the perimeter on the first one is going to be 26 centimetres. So 26 centimetres. If we look at this one, we've got an area of 39 millimetres squared, one side length of 3 millimetres. 39 divided by 3 is 13, so this one is going to be 13 millimetres. Perimeter, 13 plus 3 is 16, sorry. 2 lots of 16 is going to give us 32. What we have here is a square. We can see this is a square. We're shown now that these side lengths are equal. So what we want now is this side length. We learned in the video on number that to find that we needed the square root. So what we want is the square root of 121. This gives us 11. 11 squared, 11 times by 11 gives us 121. So the square root of 121 is 11. So if we wanted the perimeter of that shape, we would simply need 4 lots of 11. 4 lots of 11 is going to give me 44. So the perimeter would be 44 metres. Let's now look at a few exam style questions. You certainly will need to be fluent with working with the area and the perimeter of rectangles. It comes up in lots of exam style questions in context. So in this one it says a square has an area of 36 metres squared. We're asked to find the perimeter of the square. I will say, if in doubt, sketch it out. So here is my square. So we know each side length is the same. So that, and that are the same. And we've got now an area of 36. So each side length will simply be the square root of 36. The square root of 36 is 6. So we'll have 6 metres here, we'll have 6 metres here, and 6 on the other. So in part A, we need to find the perimeter. Well, the perimeter is simply going to be 4 lots of 6. 4 lots of 6 is 24, so the perimeter is 24 metres. We're now told the square is to be fenced. Fencing costs £21.60 per metre. We're asked in part B to find the cost of fencing the perimeter of the square if a 20% discount is given. So all we need to do here is simply take this answer, this 24 metres, and multiply it by the cost per metre. So in part B, all we do is take the perimeter, because we're simply fencing this red part right here. We'll do 24 times by £21.60. We can do that in a calculator. So 24 times 21.6 or £21.60. And that gives us now £518.40. So £518.40. We need a 20% discount. So you could find 10%, double that up and take it off, or you could simply do 518.4 times by 0.8, or find 80% like so. In the number video, we looked at multipliers. So all I need to do is multiply that by 0.8. That's the same as doing 80% of. We know that we can just type that in and that will give us that value, and that will give us £414.72. So £414.72. If you wanted to find 10%, you could simply divide that by 10. That would give you 10%, double it up, and then take that off. I just think using the multipliers is easier. In this one, we're asked to draw a square with half the area of a rectangle below. So let's start off by finding the area of this rectangle. The area is going to be 4 times by 12.5. 4 times by 12.5 is going to give me 50. So we've got 50 metres squared. Therefore, and I'll just use my therefore symbol, we'll have an area, half of that, we need 25 metres squared for our square. So what do we know about a square? We know the side length now of a square will be the same for all of these. All of these will be the same. So what side length do I need to give me an area of 25? Well, the square root of 25 is going to be 5. So we can simply say that will be 5 metres. Let's look at the next one. Slightly hard to see. It says the area of a square and the rectangle below, shown below are equal. Find the value of y given your answer in metres. So let's just go ahead and put this on. So this is going to be 5 metres. This is 1,000 centimetres. We know that there are 100 centimetres in a metre. So 1,000 centimetres will be 10 metres. Later in the video, we will look at some more metric conversions. So this here is y. So let's go ahead. The area of a square. Well, the area of a square is going to be 25 metres squared. So all we need to do is simply set up an equation. You could do this without, but we need now this area to be 25 metres squared too. So 10 times by y, which is 10y, that's the length times the width, must be equal to 25. So y will be equal to 25 divided by 10. So y would be equal to 2.5 metres. So all I've done is simply found the area for one, put it into the other, and solved an equation. You could just say, what's 25 divided by 10 and 2.5? I always think for more challenging examples, setting up an equation will help. Okay, let's see how many others we've put on there. We'll just do this one from here. So in question 7, it says, work out the maximum number of small blocks that can fit into the larger block shown below. So this is a 15 by 6. What we've got is a 3 by 2. So we're going into a 3 by 2. You won't always get nice block sizes, and it's essentially a case of looking at the ways to fit these in, such that the side lengths are factors of the numbers on the larger rectangle. So if I put these now with the 2 metres this way, we would end up with a gap because the 2 goes into 15 7 times with a remainder of 1. So what I do, I'd fit these along this way with the 3. We can see that 3 will go into 15 5 times, so we could fit 5 along that way. And 2 goes into 6 3 times, so we could fit 3 down this way. So all I've done here is simply, and I'll show you, I've taken this block and I've put them this way round, like so. So that now is a 3 by the 2. We can fit 3 coming down this way and 5 along that way, so it's simply 5 times by 3. So 5 times by 3 is going to give me 15 blocks in total. Do check with the dimensions on that because it won't always be that nice. So that's a typical example of where you're not actually simply doing always the length times the width divided by this particular area. Sometimes it'll work, but just check that they fit. So that gives us now the rectangles. Let's now look at a parallelogram. A parallelogram is another quadrilateral, so it's another four-sided shape, and a parallelogram has two sets of parallel sides. We can show parallel sides by putting angles on. So that putting arrows on, sorry. That tells me these two sides are parallel. They're also, of course, the same length, and these two are also parallel. So we've got two sets of parallel sides. What I'm going to do is quickly now just cut this triangle off here, and I'm going to put it on the other end. So if I took that triangle and put it like so, what we can see is that I've now formed a rectangle. So if I look now, that is a rectangle. So that area can come just here. The reason I've done this is to show that when we're finding the area of a parallelogram, as long as we have now what we call the base and the perpendicular height, we can simply use the formula for the area of a rectangle. This is the base and this is the perpendicular height. Perpendicular means that it's at right angles. So this is the straight up height and the base. What we don't want is the slant height. That is the slant height. We just want this one and this one to be at right angles. Once we have that, we simply multiply the two values. So in this particular case, all we would get here for the area of this one just here is 5 times by 4. So 5 times by 4, and that's going to give us 20, and the units are millimetres squared. So it says explain why each shape is a parallelogram, two sets of equal parallel sides, and that's nice and straightforward. So this one is just 3 times by 8 or 8 times by 3. Remember, 3 times 8 is 8 times 3, so it doesn't matter which way you multiply these. 3 times by 8, that gives me 24, and the units are going to be centimetres squared. Any area is squared. We might be asked to find a missing length, exactly the same as a rectangle. We know now that y multiplied by 4 gives 36. So if I just look at that, so we've got 4y, 4 times y, remember we don't need multiplication, is equal to 36. So y is equal to 36 divided by 4. So y is going to give us 9 centimetres. This one, we know we've got a base and a perpendicular height. So all we've got here is 8 times by x is equal to 56. So x is 56 divided by 8. So x is going to be 56 divided by 8, which is 7, and that will be 7 metres. So nice and straightforward. That gives us the area of a parallelogram. Let's now look at the area of a triangle. What I'm going to do is draw a rectangle, and I'll put some dimensions on this. Let's say now that this is going to be, let's say this length is going to be, let's say that's 4 centimetres, and we'll say that this is going to be 6 centimetres. Not massively accurate, but it gives you some idea. So the area would be 24. So the area on here is going to be 24 centimetres squared. If I now drew a line from one of the corners or vertices to the other, this diagonal now cuts the rectangle in half. So now it's cut in half, we would expect this one to be 12 and this one to be 12. What this gives me now is the formula for the area of a triangle. So if I've got a triangle now and I've got a base of 6, so let's put 6 on here, and a height of 4, we can say that the area is going to be 6 times by 4 divided by 2. We halve our answer for a triangle. So as long as we've got now the base, which is going to be this one, and a perpendicular height, all we do is base times by height divided by 2. 6 times by 4 is 24, divided by 2 is 12, and this would be 12 square units. So, base times height divided by 2. So if we look at this one, we've got a base, so we've got a height. So that's perfectly fine. Exactly the same here. We've got a base and we've got a perpendicular height. That right angle shows me that. It says state the type of triangle shown below and find the area of each. So these are right angle triangles. Later in the video we will look at triangle types, but that is an example of a right angle triangle because we have the right angle just there. So let's just put that on. Let's get rid of that, that was a bit messy. That's a right angle. So all we do is base times height divided by 2. So if we look at this, it's 5 times by 6. 5 times by 6 is going to give us 30. Divided by 2 is going to give us 15, and that will be millimetres squared. This one, all we're going to have is 3 times by 5, and we need to half our answer. 3 times by 5 is 15. 15 divided by 2, 7.5, and that will be centimetres squared. We asked to find the area of each triangle below and state whether you can confirm each triangle is an isosceles triangle. We'll leave that bit as we'll come on to isosceles triangles later, but all we need for the area is now the base, which is just here, and a perpendicular height. We've got a base and a perpendicular height. We've got a base and a perpendicular height. So in this particular case, we could simply say now that the area of this one is going to be 11 times by 12 divided by 2, or you could just say it's 6 times 11. Half of 12 is 6. 6 times 11, that's going to give you now 66 metres squared. This one here, 9 times by 3 divided by 2. 9 times by 3 is 27. 27 divided by 2 is going to give me 13.5 millimetres squared. Here is a triangle just here, and I'll just put this on. We can see that these are at right angles. So if you're given a triangle like so, and you have this base and a perpendicular height, you could still work out the area. So if we just move that one out of the way. So don't panic if you see this like so. Let's say that this was going to be 5 centimetres, and this was going to be, let's say, 6 centimetres. As long as you've got this right angle here in terms of the base and height, all we would do is 5 times by 6 divided by 2, which is going to give me 15 centimetres squared. So base here, perpendicular height. And when you first see this, you think, well, surely it should keep going from there. Doesn't matter, that's what we have. The base is fine, that's 5, perpendicular height 6. Okay, let's look at an exam style question. It says draw a rectangle with an area of 10 centimetres squared and hence draw a triangle with an area of 10 centimetres squared. The way I would want to do this is to think now of the factors of 10. We certainly don't have to have integer or whole number values for the side lengths, but it makes it easier. So if we look at 10, the factors of 10, we could have 1 times by 10 or 2 times by 5. We looked at the factors of a number in the video on number. So all I'm going to do is draw a quick sketch. In terms of this, you might actually be given square paper to draw it accurately to size or to scale. All I'm going to do is put the side lengths on. So if we have now a 2 by 5, let's do that, and we can say that. I don't know why it's giving me an addition. I think I'm holding down a bit long. So all we're going to do is put on here that this is going to be 2 centimetres and this is going to be 5 centimetres. So that's my rectangle. Nice and straightforward. What we now need to do is draw, it says hence, so hence means use your last part to draw a triangle with an area of 10 centimetres squared. If we look here, this is 10 centimetres squared. So if I wanted a triangle, we would have to double one of these side lengths. Because of course, if I made a triangle from this, like so, we would only end up now with an area of 5 centimetres squared. So all I need to do is double one of these side lengths. So what I'll do is the following. If I now make this height 4, and then we still have the 5, let's put that on, that will give us now an area of 10. So all I've done is said we'll leave the base here, because remember this one is 5, probably nicer if we put that there. Let's put that, in fact we'll just scrub that out and put it at the bottom. So all we'll have, let's put that here. So this is going to be the 5 centimetres. So this is going to be the 5 centimetres. So that hasn't changed, but I've gone ahead and just doubled the height. 5 times by 4 is going to give me now 20. 20 divided by 2. The area is going to be 10 centimetres squared. And this area is going to be 10 centimetres squared. You could, of course, have done on here a 1 by 10. And then you would have had a 1 by 20 or a 2 by 10 for the triangle. Next one, draw a triangle with an area of 8 centimetres squared. So if you think about this one, what we need is a rectangle with an area of 16 centimetres squared. So if we look at the factors of 16, we can have 1 times by 16, we can have 2 times by 8, or we can have 4 times by 4. So if I look now at a rectangle, let's do the 2 by 8. So a 2 by 8 would look something like that. So this rectangle now, if this was going to be 2 centimetres and this was going to be 8 centimetres, we know that the area of this would be 16 centimetres squared. So all I'd need to do is simply draw a triangle, and that, let's get rid of that part, and then just scribble this out. That here is going to give us exactly what we need. 2 times by 8 is going to give me 16. 16 divided by 2 gives us what we need. So as you can see, that's nice and straightforward. I probably would just draw it, but hopefully that makes sense. So area of triangle, base times by height divided by 2. Let's now look at the area of a kite. A kite is similar in terms of its calculation to a triangle. What we have is the width and then the perpendicular height. So again, these two are at right angles. What I'll do is quickly show you this. So if I got this one here and we turned this now into a rectangle. So the rectangle dimensions, this is 6, which means this is 6. We would have 60 square centimetres. What I'm going to do is just put a line here, and I'm going to put a line here. If I took this part now of the kite from here and I placed that just here, that is identical. We call that congruent, and we'll look at congruency shortly. And if I took this part and put it just here, what we can see is that I've formed now a rectangle, and let's put this on, let's choose a different colour. We formed a rectangle like so, and we can see now that the height remains 10, but the width of this rectangle here has halved. So the rectangle now has a height of 10, but a width of 3. So all we do to find the area of a kite is do this length, which is the width, times by the height, divided by 2. So this one would be 6 times by 10 divided by 2. So 6 times by 10 divided by 2 is going to give me 30, and that will be centimetres squared. This one is going to be 5 times by 13 divided by 2. 5 times by 13 is 65. Half of 65 is 32.5 millimetres squared. Always squared units for area. Okay, let's now look at finding missing lengths. This is slightly more challenging. So what we could do on this one, it says find the value of x and y in the diagram below. A couple of different approaches. What we could say is 8 times by y, which is 8y, divided by 2 will give us 20. So at this stage, you could either simplify and say that this is 4y, 8 over 2 is 4, or you could say now that 2 times by 20 will give us 40. So 8y would be equal to 40. Dividing both sides by 8, y would be equal to 5. So we'd say now this is going to be 5 centimetres. Alternatively, 8 over 2 is 4. Another way to think about it is to think now, if the area of a kite is going to be 20, the area of the rectangle would be 40. So 8 times by y is 40. If we look at this one here, so one way we could do it, we could say 6 times by x divided by 2. So 6x, we multiply the height by the width, then divided by 2, gives us now 27. So 6 over 2, that gives us 3x is 27. So x would be 27 divided by 3, which is going to be 9. So x is going to be 9 meters. Alternatively, you could have said now that the rectangle here, if the kite is going to be 27, the rectangle will be double that, and the rectangle will be 54. So 6x is 54. 54 divided by 6 is 9. So that is a kite. Let's look at a more challenging exam style question. In question 14, it says in part A, a kite has vertices A, 2, 1, B, 1, 3, C, 2, 5, and D, x, y. Find A value of x and y and draw the kite. So what it's telling me is that we could have more than one possible place for this. So let's just go ahead and put these on. So A is 2, 1. Hopefully you can see this. This is 2, 1. B is going to be 1, 3. That's going to be just there. C is going to be 2, 5, which is going to be there. So what we want to do now is draw a point D such that this is a kite. I think the easiest place to put it is going to be just here. So we can put it just here, and we've got the coordinates here, and we can say now that that point is going to be 3, 3. So let's just go ahead and draw that. So we've just plotted these coordinates. So if we go ahead, that's what we have. We could have had D out here if we wanted, and then connected up here. That's just one example. So that is the kite. In part B, we're asked to find the area of a kite. So I'll count the squares. It looks like we've got here going 2 across and 4 up. So all we would do is now the 4, and we would multiply that by the 2, and we would divide this by 2, and that's going to give me now 4 units squared. In part C, it says the lines AC and BD intersect at the point P. We need to write down the coordinates of P. So remember, this is A, this is B, this is C, and this is D. So the lines AC, all this means is the line from A to C. That's the line from A to C. This is BD, so this is the line from B to D. Intersect means they cross and they meet just here. So if we look, we've got 2, 3. So P will have the coordinates 2, 3. So a nice little question in context looking at kites. Right, let's move on now and look at a trapezium. A trapezium is another example of a quadrilateral. So a trapezium has 4 sides. A trapezium has one set of parallel sides. So if we put this on, this is an example of a trapezium, and we've got the parallel sides just here. We might have a right trapezium. That means that it's got a right angle in, and it will look something like so. So that is the example where we have a right angle. Again, 4-sided shape, and we've got now one set of parallel sides. So if I put that here, these two are going to be parallel. The formula used to be given in the formula book. What it used to say is if we had now A, this length here, B, and we had a perpendicular height, so this height H, so let's put this on, and we'll put this here, that the area was equal to A plus B over 2 times by the height, or some form of this. The way I like to think about this now is it's the average of the 2 parallel sides multiplied by the perpendicular height. So when we find the average, we add the 2 together and divide by 2. So if we look now, we're asked to find the area of each of these trapezium. So we got the two parallel sides. So for average, if we do 3 plus 5 divided by 2, 3 plus 5 is 8. 8 divided by 2 is going to give us 4. So all we do is 4 multiplied by the perpendicular height. So 4 times by 4 is going to give me 16 centimetres squared. If we look at the next one, we've got now 7 plus 10. 7 plus 10 is going to give me 17 divided by 2. 17 divided by 2 is going to be 8.5. We take the 8.5 and multiply it by the perpendicular height of 6. 6 times by 8.5, that's going to give me what, 51 millimetres squared. You can of course do that on a calculator. If you want 8.5 times by 6, let's put in 6, we get 51 and the units will be millimetres squared. Often if students forget this, what they could do is split this up into rectangles and triangles. So if we look here, we could split this into a rectangle. What we would have is a 3 by 4 rectangle, and then this side length is going to be 1. This side length is going to be 1, and you could find the area of these two triangles. So if you're ever stuck and you can't remember that formula, then what we have here is a 3 by 4, a 1 by 4 and a 1 by 4. This one you could split into a rectangle and a triangle. The triangle just here is going to have now a base of 3. That's the difference between 7 and 10. So you've got a 7 by 6 rectangle plus a 6 by 3 triangle. Either way around, that's what you would have. Let's look at this one just here. What we've got now is a trapezium, and we need to find the missing length. So it says find the value of x in the diagram below. So if we were to do this by setting up an equation, what we would say is that the two parallel sides, 8 plus 12, divided by 2, multiplied by x, gives us 60. So if we look at this, what we have, 8 plus 12, well 8 plus 12 is 20. 20 divided by 2 is going to give me 10. So 10 times by x is going to give me 60. So x will be equal to 60 divided by 10. So x is going to give us 6, and that's going to be centimetres. So I know if I add these two together and divide by 2, multiply it by this height, it will give me 60. So I can work that backwards. So that's finding a missing length. So that now gives us the area of a trapezium. Again, make sure you have the perpendicular height instead of the slant height. Let's now look at the area and perimeter of composite or compound shapes. So a composite shape is made up of one or two or more shapes. So we can see here now that this is two rectangles. So if I look here, I've got one rectangle here and one rectangle here. The easiest way to do this is by counting squares. So if we look at this one, we've got 2, 4, 8 squares. So we're asked to find the area. So the area is going to be 8 square units. The perimeter, we just count up. When you're doing this, I strongly suggest now you just follow it round, because often students forget side lengths. 2, 4, 6, 7, 11, and then we're going to get 15. So the perimeter, the distance around the outside, the perimeter will be 15 units. If we don't have squares, what we need to do is look at the dimensions. Firstly, all of the dimensions are on here. Just check that they are. We can see that we've got this one which is going to be 2, this one which is going to be 4, this one which is going to be 3, this one which will be 1, this one which is going to be 5, and this one which is going to be 5. In terms of finding the area, we've got a few different choices. What I could do is cut this into two rectangles. This would give me a 2 by 5 centimetre rectangle and a 1 by 3 centimetre rectangle. Alternatively, I could cut it just here. If I cut it just here, this would give me a 4 by 2 centimetre square rectangle. So 4 by 2 and a 1 by 5. Alternatively, I could simply turn this now into a square in this particular case, or if it wasn't, it would be a rectangle, 5 times by 5, and then I would take away a 4 times by 3 rectangle. So all I'm going to do is choose one of those. I'm going to do this one just here, and I'm going to split this up. So what we'll have is the following. We've got now on here the dimensions. We've got a 5 by a 2. So this is going to give me 5 times by 2. That will give me 10 centimetres squared. Here I've got the 3 by the 1. So we're going to have 3 centimetres squared. Do check you're using the correct dimensions. So the overall area is going to be 10 plus 3, which is going to give me 13 centimetres squared. The perimeter, if we just go ahead and collect this up, that will be 2, 4, the 3, the 1, the 5 and the 5. So that gives me 6, 9, 10, and then we're going to have 20 in total. So the perimeter, let's just put this on, perimeter is going to be 20 centimetres. That gives me 6, that gives me 9, that gives me 10, 15 and 20. With this one, what we need to do is put on the dimensions. So we'll do both the area and perimeter of this. If I now just look at what we've got here, we know that this length is going to be 8. So this whole length is also going to be 8. We can see that part of that is just here, and that length is 4. So if this one is 4, this one will also be 4. They won't always be the same, but that just gives us now that this length is going to be 4. If we now look at this side, we can see this whole length just here is the one we need to find. Well, we've got 5 just here, and then we've got 4 just here, which of course I could put there. 5 and 4 gives me 9. So this whole side length is 9. Make sure you have all of the side lengths on. So this is going to be 9 units. So all we need to do here is work out the area. We'll do the area and the perimeter. So what I have here is the 9 and the 4. So let's just highlight that. We've got the 9 and the 4. So the area of this rectangle is going to be 36 square units. Then on the next one, we have now this one, which is the 4 and the 5. So all we do is multiply the 4 and the 5. 4 times by 5 is going to give us 20. So the total area is going to be the 36 plus the 20, and we say this is 56 square units. The perimeter is the distance around the outside. So checking we've got all of these on. 4, 8, 12, 17, 25, 34 units. So the perimeter is going to be 34 units. So those are composite or compound shapes. A nice one that they often do is they give you the front of a house and ask you to work out now the total area. So let's say we've got something like this, and these two side lengths are the same. So it's a triangle on top of a rectangle or a square. So let's put that on. And what you'll be given are, you'll be given a height, so you'll be given an overall height. Then you'll be given now this side length, and you'll probably be given this one. So let's put some dimensions on this and look at finding the area of the shape. So let's say that this was going to be, 10 centimetres. This was going to be, for example, let's say that's going to be 6 centimetres, and this one is going to be 5 centimetres. What we do is look to find the area of this rectangle. So this would be a 6 by 5, so that would be 30 centimetres squared. what we would then do is find the area of the triangle. If we consider now the height and the length of this, we know that this one here is the 5 as they share this length. And then what we'll have is this height here. So on here, we know that this is 5, so that's 5 centimetres. If this is going to be 6 and this is 10, the difference between the two is going to be 4. So this one is 4 centimetres. So the area just here is 5 times by 4 divided by 2. So this is going to give me 10 centimetres squared. So the total area is the 30 plus the 10. So that gives me 40 centimetres squared. So that's a nice example. You just split it up, and as you can see here, a shape like this, split it up into rectangles and triangles. Okay, let's now look at circle parts. Circle parts, we're going to do this before we look at the area of a circle. So here is a circle, and the first thing I'm going to do is put the centre on. The centre is in the middle. What we're now going to draw is a line from the centre to the circle. We call this a radius. So a radius goes from the centre to the outside. This distance around the outside, this right here, the pink part, or it looks white, is what we call the circumference. The circumference is the outside of the circle. So the distance around it will be the circumference. What I'm now going to put on is what we call a diameter. A diameter goes through the centre from the circumference to the circumference. The diameter is twice the length of the radius. So if this was 4, this would be 8. So that is a diameter. The next thing that I'm going to put on now is what we call a tangent. A tangent is a straight line that touches the circle. It doesn't pass through the circle, it just touches it. This is a tangent. The next thing we're going to put on is what we call a chord. A chord is like a diameter, but it doesn't go through the centre. So that is an example of a chord. A chord could also be like so. So it goes from the circumference to the circumference without going through the centre. So if we label these up, let's just put this on. So this here is a radius, so that's the radius. This is going to be the centre, so centre, just there. This is a diameter, so diameter. This is going to be now the tangent. This is the chord, so let's put the chord, C-H-O-R-D. We've got the circumference, and we'll put that on. Let's look at 2 or 3 more things that you might be expected to know. The first one, if we have now a radius and a radius, the area, and I'll just scribble this on, the area trapped between these will give us now what we call a sector. So this blue part, which is part of the circle, is a sector. So we'll look at finding the area of a sector shortly. What I'm now going to do is look at this part right here and the area trapped between the chord and the circumference is called a segment. Often I think about now one of those chocolate oranges. When you break it up, you get a segment. Finally, what we'll look at is what we call the arc. The arc is part of the circumference of a circle. So this green line just here, from that point to that point, this is called an arc, and that is a length. So they are the parts of a circle. Let's now look at finding the area and the circumference of a circle. The area is the space trapped inside. The circumference is the perimeter. It's the distance around the outside. We're not given the formula in the formula book, so we must learn this. The area is given as pi r squared. All this means is pi times the radius, and I'll just write this out, pi times the radius times the radius. Pi is just a number. If you don't have pi on your calculator, you take pi to be 3.14 or 3.142. Pi, we hit shift and then the 10 to the power button. That is pi, and when we hit S to D, we can see that it's 3.14. Sometimes, if it's non-calculator, you will work in terms of pi. That's perfectly fine. So that's the area of a circle. The circumference, or the distance around the outside, can be given either as 2 pi r, or we can write this now as the circumference is pi d, pi times the diameter. We know that a diameter is twice the length of the radius. So all this is saying now, the distance around the outside is 2 times by pi times by the radius, or we can say now the circumference is pi times the diameter. So as you can see here, 2 times the radius is the same as the diameter. So it's entirely up to you what you want to use. So if we look at the first one now, we'll find the area and the circumference of each of these. So I'll do this one just here. The area is going to be equal to pi times the radius squared. The radius here we're told is 4 millimeters, so that is 4 squared. If I type this into a calculator, 4 squared is 16. 16 times pi will give me on the calculator 16 pi. This is what we call an exact value, and it's easier to work with. So if I type this in, pi times by 4 squared, this gives me now 16 pi. 16 pi is 50.3 correct to 1 decimal place. So this is going to be 50.3, and that will be millimeters squared. Remember, an area is always squared. The circumference, we're going to have now 2 pi r, or pi times the diameter. So if we've got now a radius of 4, then we've got a diameter of 8. So we could just do 8 times by pi, or we can do 2 times by pi times by the radius. So if I write this in, let's put this in. What we've got here is 2 times by pi times by 4. 2 times by 4 is 8. 8 times by pi is going to give me 8 pi on the calculator. So let's go ahead and we can just show that. So 2 times by pi times by 4 gives me 8 pi, and we can see that that's 25.1. So 25.1, and that will be millimeters, and that is correct now to 1 decimal place. I'm just rounding these to 1 decimal place. You'll be given a level of accuracy in the exam. So 25.1. We can see here that this is 16 pi and this is 8 pi. Generally speaking, the circumference won't be half the area. This is just a particular example. So on the next one, if we wanted the area is going to be pi times by 5 squared, which is going to give me 25 pi, and that would be centimeters squared. So if you're asked to leave your answer in terms of pi, this is what we'd do, 25 pi centimeters squared. The circumference would be 2 times by pi times by the radius, so this would give me 10 pi, and that would be centimeters, as that is a length. Okay, here what we've got now is, again, finding the area and the circumference. This time we have now the diameter. So on here we've got a diameter of 12 centimeters. That means that the radius would be 6 centimeters and 6 centimeters. So we need to halve this if we're finding the area. So the area is given as pi r squared. So in this particular case, we'd have pi times by 6 squared. So that's going to give me 6 squared is 36. We would get 36 pi on the calculator, as we can see if I do that. So if we hit shift, pi times by 6 squared, 36 pi, and that gives me 113.1. So this is 113.1, and that would be centimetres squared. For circumference, we can either do 2 times pi times the radius or pi times the diameter. In this particular case, it would be pi times by 12. So that's going to give me now 12 pi. On the calculator, we can do that. So 12 pi is going to give me on here now 37.7. So that's 37.7, and that will be centimetres, again, correct to 1 decimal place. Right, let's just have a look at this one just here. So we're asked to find the area, and I'm going to put this as the perimeter. Let's change this to perimeter. So perimeter of a semicircle with a radius of 9 centimetres. If in doubt, sketch it out. So what we're going to do is just go ahead and draw this. So what we've got then, this is our circle, and what we would have on here, if we drew now a diameter, this would cut this into a semicircle. So if we look now, what we have is the following. We have a radius of 9 centimetres. So if I wanted to work out the total area of the circle, we could say now that the area was going to be pi times by 9 squared. 9 squared is going to give me 81, so we'd have 81 pi. So if I just wanted half of this, all we would do is simply half our answer. So we can say now that the area of this part right here would be 81 pi divided by 2. So in a calculator, we could do this in lots of different steps. It's entirely up to you, or you could just put it in as a fraction. 81 pi divided by 2, and that's going to give the area of the semicircle 127.2. So 127.2, and that would be centimetres squared. So that's the area. What we're now looking for is the perimeter of this semicircle. So if I just now lose the bottom half of this, what we're looking for is the distance now around the outside. So what I want is the arc length. The arc, remember, is part of the circumference, and then I'm just going to add this bottom line. We know now that this is 9 centimetres and this one is 9 centimetres. So all I need is this length right here, and then I'll add now the 9 and the 9 to give me the length here. So if we do that, we know that the circumference of the whole circle, the circumference is 2 pi r. So the circumference of a whole circle would be 2 times by pi times by 9. 2 times 9 is 18, so this would be 18 pi. That would be 18 pi centimetres right the way round. So half of it is going to be 9 pi centimetres. So if I want now the total distance around this, all I'm going to do is put the perimeter is going to be equal to 9 pi centimetres plus 9 centimetres plus the other 9 centimetres. So if we work that out, let's go ahead and look at that. We've got 9 pi plus the 9 or plus 18 if you wish as a diameter, and that gives me 46.3. So that'll be 46.3, and that will be centimetres again. That is correct to 1 decimal place. Let's have a look now at a question in context. We'll do one of these. Let's have a look at this one. So it says the circle just here is a garden with radius of 5 metres. So let's just put that on. So what we've got is a radius of 5 metres. So just write in here 5 metres, and it says Fred the gardener needs to put a circular fence around the outside. The fencing is sold in 2 metre packs and costs £31.25 per pack. We need to find the cost of fencing the garden. So what we're looking for is now the circumference of this circle. So we know the circumference is equal to 2 pi r. this will give me the distance around the outside. So the circumference is 2 times by pi times now by the radius, which is 5. So the circumference is going to be 10 pi. So 10 pi, hopefully you're comfortable with 10 pi. It's just 10 times by 3.142. And we can see now that gives us 31.4. So 31.41 and so on and so forth. So we can say now that it's 31.4 ... meters around the outside. So all I've done is just found this distance right here. So all we need to do is simply now take 31.4 ... and divide this by 2. This will tell me how many packs I need. So if I divide this by 2, that's going to give me now 15.7. So 15.7 ... I'm going to use my therefore symbol. If we need 15.7 packs, we need to buy 16 packs. So we need to round up. It wouldn't get done in 15, so we need 16 packs. We take 16 and multiply this now by 31.25. What's that going to be? Bang on 500. Let's just do this in a calculator. 16 times by 31.25. It gives exactly £500. So that's what we would do for that particular question. So this is a question in context. You might be asked to find the area or perimeter. We simply do the calculations and then go ahead and multiply it up. So the area and the circumference of a circle. Let's move on now and look at what we call arc lengths and areas of sectors. So if I take now a circle, let's get a circle up here, that's a circle. We've already seen circle parts. We've seen now that this is a radius and this is a radius. The arc length, as we saw earlier, is just part of the circumference. It's this distance from here to here. So this now is the arc and we could find its length. Inside here, what we have now is the area, and this is the sector area. So we can say now that that is the sector. What we're going to do is look at finding now the arc length and perimeter of each sector and the area. What we've got here are circles and they've been cut up. Hopefully we know that there are 360 degrees in one complete revolution around a point or in a circle. So let's start off with the area of this one just here. What we've got is 90 degrees of it. We could just find the area of the whole circle and divide our answer by 4. The reason being 360 divided by 90 is 4. So the area of all of this circle would be pi times by 6 squared. So the area of the whole circle would be 36 pi meters squared. So the area of this one would simply be 1/4 of this. So we would have now 9 pi meters squared. So if we look at 9 pi is going to give us on here 28.3 meters squared. So I found the total circle, and let's see if I can put the circle on this to hopefully show what I've done. Let's see if it'll show that. So what I did, let's say that's just there. I've found now all of this circle and I've just divided my answer by 4. If we look now at the arc length, this distance from here to here, we know that the circumference of the circle is given as 2 pi r. So the whole thing would be 2 times by pi times by 6. That would give me 12 pi. We've only got 1/4 of that. So 1/4 of that, 1/4 is going to be now, therefore, we're going to have 3 pi meters. So 3 pi meters, let's put this in here. Let's grab that back up. So 3 pi meters is going to give me 9.4, and that's to 1 decimal place. So 9.4 meters. That is this arc length just here. So that's the part that I've just found. If I wanted the perimeter of this particular sector, then the perimeter would be the 9.4 meters plus 6, as we would need now this radius added. So we'd need this one plus this one. So do look out whether it's asking for just the arc length or the perimeter. So that's what we get. Ideally, when we're dealing with these, the angle is a factor of 360 degrees. So if we look now at, and let's just, we want to get that back. Let's now look at this one just here. So 30 degrees, 360 divided by 30 is going to give us 12. So what we could do, let's just put that on, we could find the area of a circle and divide our answer by 12. 360 divided by 45 gives us 8. So 360 divided by 45 gives us 8. So again, we could find the area of a circle and divide our answer by 8. This one, 150, isn't a factor of 360. What we could do instead, and generally speaking for arc lengths and areas of sectors, all we would do for the area of a sector, this would be the angle, which in this case would be 150 of 360 multiplied by pi r squared, because we've just got now a fraction of it. The arc length, so I'll call this L, would be 150 of 360 multiplied now by 2 pi r. We're just finding a fraction of the circumference. Remember, this is a fraction of a circle. Of in maths, it's multiply, so that's what we get. So generally speaking, if we have an angle here and we call that angle theta, let's just change this over. So let's put this angle here and we'll say that this is the radius. Let's say that we've got an angle and this angle here is theta and this length is r. We can say that the area of that sector is going to be theta over 360 multiplied by pi r squared. We can say that the arc length is going to be that angle, theta over 360 multiplied by 2 pi r. Hopefully, as I say, in this particular course, we've got now a factor of 360 and we can just divide our answer. Alternatively, you can just take the angle and multiply it. So that now gives us the area of a sector and the length of an arc. Let's now move on and we're going to look at sketching the net of a cube or a cuboid. So let's first look at the idea of a cube or a cuboid. This is an example of a cuboid. A cuboid is a 3D shape and we call this a prism. What we have with a cuboid is a rectangle on the end and we have a constant cross section. So wherever I move this rectangle through the shape, it remains the same. So we've turned a rectangle into a 3D shape, and with all prisms we have a constant cross section. A cube is going to simply be a cuboid where all of the dimensions are the same, such that we have a square on each end. So if you look at, for example, a dice is a cube because each face is a square. The face is just this part right here. So what we want to do is sketch the net of this closed top cuboid. Closed top means that it has a lid. The net is what it would look like if we unfolded it. So if I open this up, and we will assume that it's got no flaps on to glue it together, what would this look like if it was undone? So what I do is simply go ahead now and consider all of the rectangles, and we'll draw this now on the square paper here. So if I look at the base, I've got now a base of 4 times by 2. So all I'm going to do is draw a rectangle which is going to be a 4 by 2 rectangle. So if I go ahead, we'll have now a 4 by 2. That is a 4 by 2 rectangle. So this part corresponds to that one, this part corresponds to that one. What I'm now going to do is go ahead and do the front just here. So if I now open this up, we've got the 2 again here, but we have now a rectangle that is 3 high. So that's that bit done. That's not a brilliant rectangle. Ideally, ours will be a little nicer than that, and it'll look something like that. If I then consider now the back of this, which again is just going to be a rectangle, would fold downwards, and we'd have exactly the same dimensions. So what we'd have is something that looked like so. If I now folded the sides down, and let's put these on, the sides, this side and then this side are going to be the same. So if I look at this rectangle here, this rectangle is a 4 by 3. So what we'll have now, if we put this on, the 4 is just here and the 3 is like so. So that would fold out there, and then this one of course would fold out the other side. So that will fold out like that. What we have here is a closed top cuboid. That means that it's got a lid. The lid of course is going to be the same as the base. We could put the lid here, we could put the lid here, we could put it here, and we can put it here. I'm going to put it just here because that just makes it easier in terms of the paper that I've got. So let's make that a little neater now. Let's put that on there and it'll look something like so. So what we've got then is the net. We've sketched the net of the cuboid. We've taken it from a 3D shape to a 2D shape. So this one goes with that one. We've got now this one here going with that one. We've got the back one going with that one. We've got this side going here. We've got this side going here. And then we've got the top going here. You must draw those accurately. And as stated, if you have a cube, all of these will just simply be squares. So the reason we've done this in this part is that we're now going to look at the volume and the surface area of a cube or a cuboid. So what we're looking at first is the volume. Volume is the amount of space that we can get in that 3D shape. Often you'll hear this being called the capacity. So if I now look at this, what we've got, this is an example of a cuboid. So rectangle on the front, and I'm just going to put some dimensions on. Let's say that this is going to be 5 centimetres, this is going to be 6 centimetres, and this is going to be 8 centimetres. So I've just chosen those. In general, when we find the area of a prism, and we'll look at more prisms in the next part, we find the area of the cross section. This is an example in this particular case of the cross section. So the area in this one is going to be the 5 times by the 6, which is going to give me 30 centimetres squared. Once we have the area of the cross section, we multiply it by the length of this 3D shape. So we can now write that the volume is going to be 30 multiplied by the 8, and this gives me 240, and the units are centimetres cubed. Whenever we have a volume, it will always be cubed. Units cubed, metres cubed, centimetres cubed, and so on and so forth. With a cuboid, you can just multiply all 3 side lengths. The reason I'm telling you to find the area of a cross section and multiply it by the length, that will work for all prisms. This is a cross section, so you could have done this one as a cross section and multiplied by the length. With the cuboid, it doesn't matter. So the volume, the amount of liquid or air that we could get in here, the capacity is 240 centimetres cubed. If we look at the surface area is everything we can touch, and that net is given here. So if we wanted the surface area of this, all we do is find the area of this one, 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 the area of that one, and the area of that one, and add it together. So sometimes it's easier to draw a net to find the surface area. So if I just go ahead and look at finding the surface area, the way I like to do this is as follows. What we say to ourselves is that we find the area of this face just here. Well, we can see that this is going to be 5 times by 6, which is going to be 30 centimetres squared. If I've got 30 just here, I've also got a 30 round the back. We know that those two are the same. So if this is closed top, all we're going to do is find now 2 of these. We'll have 2 of the sides and 2 of what will be the top and the bottom. So this one here, this is going to be the 8 times by the 5, so that will give me the area of that one. So we'll have the 5 times by the 8. 5 times by the 8 is going to give me 40 centimetres squared. Then we've got this one here, so let's just put around there, we've got another one of 40. Then we've got the top here. So the top is going to be now the 6 times the 8, or 8 times 6, and that's going to give me 48 centimetres squared. So if we've got one on the top, of course we've got one on the bottom if it's closed top. If it's open topped, you would leave one of those off. So all we need to do to find the surface area is double this up, so that will give me 60, double this up, which will give me 80, double this up, which is going to give me 96. So if we add all of this together, that's going to give me, what's that? That's 140 and that's 236. So that would be 236 and it's centimetres squared. Surface area is always going to be squared. Volume is cubed and surface area is squared. So you find one of these and double it up, find one of these and double it up, find one of these and double it up. So you've just got all of the dimensions multiplied by one another and doubled. If you want to draw nets, you can do it that way. I just think it's easier to consider now the different faces. So let's look at a typical exam style question. It says an open top box is shown below. So we've got this cuboid, 2 times 3 times 1. We need to find the volume of the box. So all I'm going to do is find the area of a cross section. So the area is going to be 3 times by 1, which is going to give me 3 metres squared. So the volume is going to be this area multiplied by the length, 3 times by 2, so that's going to give me 6 metres cubed. You could have done that any way round. Let's now find the surface area of the box. So this one right here, that is going to be now 3 times by 1, so that's going to be 3 metres squared. If we look at this one, this is going to be a 2 by 1, so that's going to be 2 metres squared. And then the bottom is going to be the 2 by 3, and that is going to give me now 6 metres squared. We need to be careful here. This is open top. So I need a 3 and a 3. I need a 2 and a 2, and I just need one of the 6's because this part isn't there. It's only now the bottom that we've got. So the area is going to be 6, then we're going to have 10 and we're going to have 6. So this is 16 metres squared. So hopefully you can see what I've got. I've got 2 of these, 2 of these and 1 of these, and I would show a bit more working if this was an exam, but we've shown more working on this one. So we've done that, done part A and part B. It says in part C, paint costs £2.10 a tin and each tin covers 1.5 square metres. We're asked to find the cost of painting the outside of the box. So what we need to do is simply consider the surface area. So we know we've got 16 square metres to cover. Each tin covers 1.5 square metres. So this will tell me how many tins I need. 16 square metres. How many times does 1.5 go into 16? So what have we got? 16 divided by 1.5. And that gives us now 10.6 and so on and so forth. So 10.6 recurring. Therefore, we need now 11 full tins. We can't do it in 10. So all we need to do then is 11 times by the £2.10 So if we do 11 times by £2, what's that going to give me? £23. And what are we going to get on that? 23, let's just put this in, I don't know why I can't work this out in my head. £2.10, 23, 10, 23.10, there we go. So that's going to give £23 and 10p. So nice and straightforward, nice and logical. Don't write down £23.1, put £23.10, and certainly don't put £23 and a penny. So that's a nice question looking at a cuboid. Okay, let's look at this one. So in here we're asked to sketch a cube with a volume of 27 cubic centimetres. So in the number video we looked now at cube numbers and cube roots. All we need to do to find the side lengths of this, and if I quickly draw this up, what we've got is a cube. So if, let's just copy that, this will make it easier and make it more accurate. So in this particular case, we've got now, this is the cube. I'll make it look hollow. Each of these side lengths is going to be the same as it's a cube. So unlike a cuboid is a rectangular prism. This is a square prism. So each of these are the same. So this one just here, this would be x, this would be x, and this would be x, with x all being the same. So here, all we need to do is take the cube root of 27. That will give me these numbers, 3 of them, that will multiply to give 27. So shift and then the cube root, if we looked at this on the number video, that gives us 3. So what we can say is each side length is going to be 3. So all we'd need to do is put 3 on each of these. And of course, don't need the x's, but that's what you do. So you could say x cubed is 27. So this is going to be 3 centimetres, 3 centimetres, and 3 centimetres. Out of interest, if we were asked to find the total surface area of this and it was closed top, we know that each of these is the same. Each has an area of 9 centimetres squared. So all we would do is 6 times 9, because 6 of them are the same, so that would give us 54 centimetres squared. So if you're asked to do that, that's what we would have. So that gives us now the volume or the capacity of a cuboid and the surface area of a cuboid. Let's move on now and look at the volume of a prism. A prism, like a cuboid, has a constant cross-section. My favourite way to show this is to think about the different Smarties boxes. The original Smarties box was a tube. A tube is a cylinder. On the end you have a circle, and that circle remains right the way through. They changed them to hexagonal prisms. So there's a hexagon on the end, and that went right the way through. They also did smaller boxes, which were cuboids or a rectangular prism. So the rectangle is the constant cross-section. So here we've got a cube, a cuboid, a triangular prism, and a cylinder. So the cylinder has a circle on. You used to be given the formula in the formula book for this. You're no longer given that. So what we've got now is that the volume of the prism is the area of the cross-section multiplied by the length. And that's why in the last example here, I said the area of the cross-section multiplied by the length, instead of just multiplying the 3 sides. So if we had, for example, on this one, that this cross-section here was going to be 10 centimetres squared, and this length was 3 centimetres, then the volume would simply be 30 centimetres cubed. So all I've done is taken the area of a cross-section and multiplied it by the length. So with this triangular prism, we could find the volume. So if we look at the area of the cross-section is the triangle. This isn't a cross-section. The rectangle isn't a cross-section as it's not constant right the way through. So here, the area of the rectangle, 5 times by 2 divided by 2, this would give us 5 centimetres squared. So that is the area of the cross-section, like so. That's this part. And then all we would need to do is multiply our answer by the length. We've got the length here. The length is going to be 4. So to find the volume, we would simply do 5 times by 4, and that's going to give us 20, and that will be centimetres cubed. If you want another example of a prism in real life, a Toblerone box is an example of a prism. So that's a triangular prism. Triangle on the end and then a constant cross section, and you'll have a length. These shapes are not prisms as they don't have a constant cross section. So for example, this is a pyramid. So on the end we would have, for example, a square, but that square doesn't maintain its shape right the way through. These cones just here, again, circle on the end, but they're not now prisms. So area of the cross section multiplied by the length. Let's now look at another type of prism, which is a cylinder. I split this up because cylinders are just slightly more challenging. So let's start off by looking at the volume of a cylinder. Again, the volume is the capacity of it, or how much space there is inside. So think about the air or the liquid that we could get in here. All we do is find the area of the circle on the end and multiply it by the perpendicular height. So in this particular case, we would find the area of the cross section, and in here the cross section is going to be a circle. Once we found the area of this circle, we multiply it by the height. So we can see now that the area of this would be pi r squared, so that would be pi times by 5 squared. So the area will be 25 pi. The volume is just going to be 25 pi multiplied by the height, which is 12. This is going to give me 300 pi. So if I did this on a calculator, and of course you can do this step by step, you can do 12 times by 25 pi. That's going to give us now the 300 pi. 300 pi is going to give us 942.5. So 942.5, and that will be centimetres cubed. Generally speaking, the volume of a cylinder is given as pi r squared height. So you take the area of a circle, pi r squared, and multiply it by the height. Remember, we looked at algebra. We said now that if we're multiplying, we don't need the multiplication symbol between the letters. So that's all we would do. Now, that is the volume. The surface area is more challenging. So what we're going to do is split this up, and imagine this is a baked bean can. With a baked bean can, if we split this up, we would have now a circle on the top, we would have an identical circle on the bottom, and then we would have a rectangle, and that would be the main piece of the tin. So it looks something like this. So if we put this on, something like so. So we would have now these three sections. If this was open topped, we would only have one circle in terms of the surface area. This is where it gets quite tricky. Let's look at the dimensions on here. Firstly, we know that the radius is going to be 5. So this radius is 5, and clearly this radius too will be 5. So if we put on here, so the area of this circle here, we know is going to be pi r squared. So this would be 25 pi centimetres squared. We worked that out just here before. So if that one is, of course, this one too is 25 pi centimetres squared. This is the tricky part. We've got now this height, and we know this height is 12 centimetres. That is perfectly fine. But what we need is this length right here. You'll notice that when you split that bean can up, this wraps around the circle, and that is a circular lid. Therefore, this length is the circumference of a circle. We know the circumference of a circle is 2 pi r. So what we'll have, this length right here will be 2 times by pi times by 5. So the circumference of a circle is going to be 10 pi centimetres. So this is 10 pi centimetres, that length right here. So the area of this is going to be 12 times 10 pi, which is 120 pi centimetres squared. So all we do is find the circumference of a circle, and that forms that line. Therefore, the total area of the closed top cylinder will be equal to, so total area will be the 25 pi on the top plus the 25 pi on the bottom plus the 120 pi in the middle just here. So this will give us a total of 170 pi, and that will be centimetres squared as it's an area. And of course you could find the value of that using the S to D button in terms of a decimal answer. If it was open top, we would just get rid of one of the circles. In general, we could say that the area was equal to 2 lots of pi r squared plus 2 pi r h. This is the general formula. I personally wouldn't look at remembering that. I would just find the area of each circle and the area of the middle section. So that's what we've got. Let's just do one problem in context. So Fred is making a circular cake with a radius of 12 centimetres and a height of 20 centimetres such that it makes a cylinder. So let's just draw this. We're not asked to draw it. I think drawing always helps in these particular cases. So that's going to be the top. Let's grab that, and that will be the bottom. So we've got now a radius of 12 and we've got a height of 20. So if we put the sides on, the cake will look something like so. So not a brilliant diagram, but enough for us to work with. So let's put this on and this on. So we've got the radius. So with the radius, we can have it on the top or the bottom. It really doesn't matter. And then we've got now a height. So if I put the values on here, we can say now that this is going to be 12 centimetres and this is going to be 20 centimetres. So it says find the area of the top surface. So the area is simply going to be pi r squared, so pi times 12 squared. That's going to give me 144 pi. 12 squared is 144. So 144 times by pi, and that will give us now 452.4. So 452.4, and that will be centimetres squared, correct to one decimal place. So that's just now the area of the top. We need to find the volume. So all the volume is going to be is the 144 pi, and we need to times that by the height, which is going to be 20. So our answer in here, we just times by 20. So multiplying by 20 gives us 2,880 pi, and that would be centimetres cubed, which we could write now as, let's just hit S to D, 9047.8. So 9047.8 centimetres cubed. In part C, it says cake mixture costs 16p for every 300 centimetres cubed. We're asked to find the cost of making the cake to the nearest penny. So all we need to do is divide, and we will assume that this doesn't come in boxes of 300 centimetres cubed. We're just given this. So all we would do is our value just here. So we could say now the cost is going to, what have we got? 300. So let's work this out. We've got now this value or this value. So we got the 9047.8 ... and we need to divide this by 300. So let's do that. If you wanted to store this in the calculator, you could hit Shift Store A. That will hold it in here. And then if you wanted to bring it back, it's Recall A. So that'll stay in there. If we divide this now by 300, that gives me now on here 30.159. So this is going to be now on here. So let's say 30.159 dot, we need to times this by 16p, as we need 30.159 lots of this. So if we go ahead, times this by 16p, so 16p, and that gives us now 482.5. So that's going to be 483p, or £4.83 to the nearest penny. So a typical question, we will assume that this isn't sold in boxes of 300. We can just get this at that price. If it said boxes of 300, then we would need 31 boxes, and we'd multiply the 31 by 16. So that is the volume and the surface area of a cylinder. Let's now move on. What we've got here is a cone. A cone isn't a prism. When we're looking at the volume of a cone is simply 1/3 of a cylinder with the same dimensions. You will be given the formula for this in the exam. The volume is given as 1/3 times by pi r squared height. So pi r squared height gave us now the volume of a cylinder. A cone is just 1/3 of that. What we need when we're finding this now is the radius and the perpendicular height. What we don't want is the slant height, and the slant height is this one just here. If you're given the slant height and you need to find the volume, you will have to use Pythagoras' theorem, which we will look at later. But in this particular case, all we would simply do to find the volume of this cone, the volume would be 1/3 times by pi times by the radius squared times by the height, which is going to be 12. So we could put this straight into a calculator. In terms of way in which you type this, you could just write it now as pi. So we hit shift pi times by 9 squared times by 12 divided by 3. That's just saying 1/3 of this. So that gives me 324 pi. So 324 pi centimetres cubed. That's in terms of pi. So if we hit the S to D, that's 1017.9. So 1017.9, and that's centimetres cubed, again to 1 decimal place. So that's the volume. If we were given the diameter, we would have to halve our answer. So you'll be given that formula. All you do is simply substitute the numbers in and find the value. Okay, we're now going to look at the curved surface area of a cone. This is a slightly trickier thing, and the best way to think about it is if you've ever been to the seaside and got chips in one of those cones. When we're looking at one of those, if we turn it upside down, it looks something like this. It's open topped. When we're finding now the surface area, it is just the curved surface area. So we're not now adding a top unless we're told to. If we're told it's closed top, then we will add a circle to it. The formula that you'll be given for the curved surface area, so just the outside, this part, is pi RL, or pi LR. This is pi multiplied by the slant height multiplied by the radius. So this time we need this slant height and we need the radius. It's not the perpendicular height. So if we wanted now the curved surface area of this open cone, we would say that the area is pi times by 15 times by 9. So 9 times 15 is 135. This would be 135 pi, and this would be centimetres squared, because it's now an area. Of course, if you wanted now it to be closed top, all we would do to this is just add pi r squared. So all we would do is add now the area of a circle, so that would be pi times by 9 squared, which would give me 81 pi centimetres squared. So if it was closed top, we would add these two together. If it was open topped, we would just have that part right there. So in this question it says find A, the volume, and B, the surface area of the open top cone below. The cone has diameter 12 centimetres. So straight away what I'm going to do is put that the radius is going to be 6 centimetres. So let's start off by finding the volume. The volume is 1/3 times by pi r squared height. This is what you'll be given. So the volume is 1/3 times by pi times by 6 squared times by the perpendicular height, which is going to be 8 centimetres. So we can put that in a calculator, and if you wanted you could type the fraction of a third in. So instead of dividing by 3 we could just simply type 1/3 times by pi times by 6 squared times by 8, and that gives us now 96 pi, and that's 301.6, so 301.6 centimetres cubed, correct to 1 decimal place. If we look at the area is pi multiplied by the slant height multiplied by the radius. So we can say that the area is going to be pi times by 10 times by the radius, which is going to be 6. So the area is going to be 60 pi. That's going to be centimetres squared. And again, we can get a decimal answer for that. So that's 60 lots of pi. So 60 pi is going to be 188.5. So this is 188.5, and that will be centimetres squared. So that is a cone. It is 1/3 of the volume of a cylinder with the same dimensions. If you want to test that out, you can do. You can get a cylinder and get 3 of these cones, and you can pour the entire content of a cylinder into those 3 cones, or vice versa. You can fill a cone up 3 times and fill a cylinder of the same dimensions. Right, let's move on, and we'll look at the volume of the pyramid. Very similar format to what we looked at before. You'll be given now the formula, and again it's a tough one here. You'll be given 1/3 base times by height. So if we look here, what we have is a base. The base in this case is a 6 by 6 square. So all we would do is simply say now that the volume is going to be 1/3 times by the base. The base area is 6 squared, multiplied by the perpendicular height of 4 centimetres. You might have the perpendicular height shown on the outside. Again, what we don't want is the slant height. So we could go ahead and put this through the calculator. So 1/3 times by 6 squared times by 4. If you wanted, you could go ahead and work that out yourself. 36 divided by 3 is 12. 12 times by 4 is going to give 48. Alternatively, you could put this into a calculator. So if we do that, let's do that. So we've got now 6 squared times by 4, and that's all divided by 3, and that gives us now the 48. So that's 48. 48 centimetres. Let's get the correct units on that. 48 centimetres cubed, as it's a volume. Again, remember all of these are going to be in centimetres cubed or units cubed. Okay, let's move on, and we will look at the volume and the surface area of a sphere. A sphere is just a perfect ball. This is again a challenging topic, but we will be given the formulae. The formula for the volume is going to be, or the formula for the volume is 4/3 pi r cubed. The surface area will be given in the exam as 4 pi r squared, where r is the radius of the sphere. So in here it says find A, the volume, and B, the surface area of the sphere shown. So we've got a sphere and we've got a radius of 6 centimetres. So the volume in this particular case will be 4/3 times by pi times by the 6 cubed. So all we need to do is simply substitute this now. I'll put this into a calculator. So we have 4, And you can do 4/3. You can type it in as 4/3, or you can do 4 times the pi times the 6 cubed divided by 3. It doesn't matter. So 4/3 times by pi times by 6 cubed. Little cube button if you want it. Here or just there, sorry, and then just put that. So you could have done that. Let's just show that. So if you wanted 6 cubed, you could have pressed that one. Or what you can do is do the 6 here and put the 3 in. It really doesn't matter. Probably quicker to do that one. So that's 288 pi. So 288 pi, and that will be centimetres cubed as it's a volume. And 288 pi on your SD is going to be 904.8. So 904.8, and that's going to be centimetres cubed. The area is 4 pi r squared. So this is 4 times by pi times by the radius squared, which is 6 squared. 6 squared is 36. 4 times by 36 is 144. So this would be 144 pi centimetres squared. Again, you can plug that into a calculator if you want. And 144 pi. So 144 pi, that's going to give us now 452.4. So 452.4, and that will be centimetres squared. So volume and the surface area. Relatively straightforward once you have the formula, and you won't be expected to know that formula. You'll just be expected to identify how to substitute into it when you have a sphere. Here it says find the surface area of a sphere that has a diameter of 10. If the diameter is equal to 10, the radius is going to be equal to 5. So the surface area is simply going to be 4 times by pi times by 5 squared. So 5 squared is 25, 4 times by 25 is 100, so we get 100 pi, and that will be metres squared. So that'll be 314.2, because pi we know is 3.14, so all we'd have is 100 pi, so 100 pi if we plug that in, so 314.2, and that would be metres squared, correct to 1 decimal place. What we've got here is a hemisphere. So it says find the volume and surface area of the closed hemisphere below. The radius of a hemisphere is 4 centimetres. So if we think about the volume, we know that the volume is 4/3 pi r cubed. If you're confident, you can just do 2/3 pi r cubed in this case. But if not, if we found the volume of the entire sphere, we would use 4/3 pi r cubed. So the entire volume, if this was a full sphere instead of a hemisphere, which is just half, would be 4/3 times by pi times by 4 to the power of 3. So if we do this now on a calculator, what we've got, and we could type it in like so, 4 times by pi times by 4 to the power of 3 divided by 3, that's exactly the same as typing this in. That would give us now 256 over 3 pi, so 256 over 3 pi. Therefore, we would need half of this, and it would simply be, now dividing this by 2 to give us the volume, that would give us 134, so 134.0, and that is going to be now centimetres, so that would be centimetres cubed, correct to 1 decimal place, as we've just halved our answer. This is now on here, it's a closed, so what we need is the surface area. So the area in general for a sphere is 4 pi r squared. So if we looked at this, what we'd have now is the area is going to be 4 times by pi times by 4 squared. So this is going to give us now 4 squared is 16 times by 4. This is 64 pi. So what we would need now is half of that for the half of the hemisphere. So if we've got 64 pi, half of that is 32 pi. 32 pi is 100.5. So we'd have 100.5 ... plus now the area of the circle, because this is closed it's got a closed one, so it's now got a circle on the end, plus pi r squared. So plus pi times by 4 squared. So I've got the surface area of a hemisphere plus the circle. So if I now plus 4 lots of 4 times by, what have we got on here? 4 squared times by pi. So let's put this in, plus pi let's put pi rather than that. That's what I need. Pi times by 4 squared, and that will do it. If you want to bracket that off, you can do. It will calculate it for us otherwise. And that will give us now 48 pi, which is going to give us 150.8. So 150.8, and that will be centimetres squared. So a much more challenging example just there. Okay, let's now move on to look at 3D solids and the properties of them. This could have appeared earlier on when we were looking at the net, but what we're going to consider now are the faces, the edges and the vertices. Faces now are just the surfaces or the panels. So this is a face, this is a face. The edge is where the faces meet. So this is an edge and this is an edge. The vertex are where the edges meet, or if you like, the corners. The plural of vertex is vertices. So what we'll do is look at this particular cuboid and we will write down now the faces, the edges and the vertices. We'll do exactly the same over here for this square-based pyramid. Faces, edges and vertices. So if we consider now the faces on this, hopefully we should know that there are 6. We've got the front, we've got the back, we've got this side, we've got this side, we've got a top and a bottom. I'm assuming it's going to be closed. So it's a solid shape with a closed top. So we've got 6 faces. If we now look at the edges, we can see now we've got one here, one here, one here, one here, that gives me 4. We've got another one here, another one here, another one here, another one here, that gives me another 4. Then we've got one here, we've got one here, one here, one here, that's another 4. In total, there are 12 edges. If we now look at the corners or the vertices, we've got one here, one here, one here, and one here, that's 4. And then one here, one here, one there, and one there, that's another 4. So there are 8 vertices. If we do the same with this square-based pyramid, we've got a face on the bottom, and then we've got a side, a side, a side, and a side. That gives me 5 faces. If we now look at the edges, we've got 1, 2, 3, 4. Then we've got 1, 2, 3, 4. So we have 8 edges. If we now consider the vertices, we've got 1, 2, 3, 4, and 1. So that gives us 5. So faces, edges, and vertices. So they are properties of 3D shapes or solids. We've half looked at that before in terms of looking at the net of a shape, but again, I've put this here. It could have gone anywhere in this particular unit. Okay, let's now move on and look at congruent or congruent and similar shapes. If 2 shapes are congruent or congruent, they are identical. That means that they're the same shape and the same size. If 2 shapes are similar, they are the same shape but a different size. One is an enlargement of the other. Their sides must stay in the same ratio. So let's look at that now, and what I'll do is draw, here is a rectangle, and what I'm going to do is put another rectangle next to it. These 2 rectangles are congruent. They are identical in size and shape. If I now get another rectangle, what I'm going to do is the following. I'm going to put it on top of that, and I'm going to do a scale factor enlargement. So if we look now, let's say that looks to be about double the size. These 2 are similar, so they're mathematically similar. These 2 are congruent, these are mathematically similar. If I'd drawn something like so, let's say I drew another rectangle and said now here that these two, well, these aren't mathematically similar because they're not in the same proportion. They're not the same shape. So they are both rectangles, but they don't remain in proportion. So here's a question here. It says shape A is shown on the grid below. We need to draw a shape that is similar to shape A on the grid. This means mathematically similar. So what it isn't telling me to do is just draw something that looks a bit like it. It means that what we need to do is draw something that has the same proportions, but either bigger or smaller. I'm going to make it twice as big. So this side length is 2, so all I'm going to do is make that 4. I'm going to double this up. Then the bottom one is 2, so we'll make that 4. I'm just doubling that up. This side length is going to be 1, so that is 2. That one is going to be 1, so I'll make mine 2. This one is going to be 1, so I'll make mine 2. And finally, we'll connect it there. Those are mathematically similar. Same shape, different size. What wouldn't be mathematically similar is me drawing something like this. So whilst they are sort of similar in a non-mathematical sense, a similar shape, they are not mathematically similar as the proportions are not the same. We can see quite clearly now that if this one is 1 and this one is 1, these should be now the same length, and they're not. Okay, so that's drawn a similar shape. Let's now look at this question. It says, study the shapes below. So here we've got 3D blocks. We're asked to circle 2 of the shapes that are congruent or congruent. So we need identical ones. These ones, these 3D shapes, they've been flipped over, but this one and this one here are going to be congruent, or we could say this one and this one. So those are identical in shape and size. So these two or these two, not that one and that one, or that one and that one, these two or these two. So congruent and similar shapes. We'll extend this now and move on and look at problem solving with similar shapes and in particular similar triangles. This is really quite tough and that's why there's a star on here. What I'm going to do is have a triangle and then I'm going to have another triangle on top, and we know that at the moment these are congruent. What I'm going to do is extend this and I'm going to double the size. So you can see now that these remain in proportion. We can see that the angles are going to be the same. One is just a scale factor enlargement of the other. So I've doubled the size. So if I said now that this was 2 units long, we would expect this one to be 4 units long, because all we've done to get from the small one to the large one is multiplied by 2, or to get from the large one to the small one, we've divided by 2. So for example, if I said now that this was going to be 6, we would expect this one to be 3, because all we need to do to get from that one to that one is divide by 2. These are similar, so we have a scale factor enlargement. So that's essentially what we do. It says the diagram below shows 2 similar triangles. 3 of the side lengths have been given on the diagram. So we got this one, and this one. It says add the following 3 lengths to the diagram such that each side length of both triangles are labelled. Let's just first look at this notation here. What it's telling me, this angle corresponds to this one, and then this angle corresponds to this one. So these are the same way around. Do check that they're the same way around. So this side length will be in proportion with this one. So those two are the corresponding side lengths. This one here and this one will again be, so this one and this one, those ones are going to be now the corresponding sides, and then this one will go with this one. So if we look at them, we've got one thing that links the two, 6 centimetres to 2 centimetres. So if I wanted to go from the larger one to the smaller one, I would divide by 3. If I wanted to go from the smaller one to the larger one, I would multiply by 3. So if we look here, we've got 8.4 centimetres. So I would want to find this length by dividing 8.4 by 3. 8.4 divided by 3 is going to give me 2.8. So straight away we can see now that the 2.8 is going to go just there. So 2.8 centimetres would go here. All we're left with now are these two just here, and this should be relatively obvious what you're doing with each. 3.2 is 1/3 of 9.6, so 9.6 would go here, and the 3.2 centimetres would go just there. So all we've done is looked at finding now the missing lengths based on one being a scale factor enlargement of the other. This is a scale factor enlargement of 3 from the small to the large, or 1/3 from the large to the small. So quite a tricky topic, but it's all about proportion. Let's now look at tessellation. The best way to think about tessellation is to think about the game Tetris. In the game Tetris, you're trying to get the blocks to fit together with no gaps. If we can get shapes to tessellate, they will fit together with no gaps. So in question 4 it says, show that the shape below tessellates by continuing the pattern using at least 5 more shapes. So all we're going to do, and I'm going to colour these in rather than draw them. So what we'll have is, the first one, we'll put this on. So that is going to look something like so. So this is going to be my first one. That's not brilliant, but it gives us some idea. What I'm now going to do is put another one of these in, and I'm just going to turn it around like so and fit it like that. So that's the next one we would put next to it. You can see now that there are no gaps between these shapes. If I put another one on, we could just now put it in this way round and put that like so, like that, and then we could have another one. Let's do this one. We can have a black one just there, and that goes like so, and then we can go ahead and do another one. Let's see, we're kind of running out of colours. Let's see if I can use the highlighter. So that one can go like so and look a bit like that. And then we'll do one more, and that'll show these tessellate. Let's just, we'll go back to red. So now we've got that and those over on there. I would do this with a pencil and a ruler, but clearly you can see now that those shapes tessellate. They fit together with no gaps between them. Right, let's now move on and look at types of angles. I've got a protractor here. I might use it. It's not the most interactive of things in the world, but we'll have a go with it. So what we're going to do is look at some basic angle facts. First thing we're going to do is look at acute angles. Acute angles are angles that are going to be less than 90 degrees. So if this will work, hopefully it will work. Okay, it's not wanting to work. Acute angles are going to be less than 90 degrees. So if I put a line just here and we do an acute angle, it's anywhere up from 0, and I'm reading round the outside of the protractor. You can see 0, 10, 20, 30, 40, 50, right the way up to 90 degrees. So any angle before 90 degrees is an acute angle. So 46, 52, 78, and so on and so forth. Once we get to 90 degrees, this is called a right angle, and we can show that just here, as we can see, with a little square. So if you're not given a size, but you're given a square, that is 90 degrees. Angles that are greater than 90 but less than 180 degrees are called obtuse angles. Once we get to 180 degrees, we have a straight line. Angles on a straight line sum to 180 degrees. Once we go past 180 degrees, we have what we call a reflex angle. So right the way round, the angle on the outside here is going to be a reflex angle. So this is an example of a reflex angle. Greater than 180 degrees, but less than 360. So if I drew this now, for example, let's say that this angle here, this looks to be an acute angle of about 60 degrees. Then the reflex angle around the outside is going to be 360 degrees minus the 60, so that would be 300 degrees. Angles around a point sum up to 360 degrees, or one complete revolution is 360 degrees. So this is the acute, this is the reflex. If we had an obtuse angle, let's do an obtuse angle. So an obtuse angle like so, let's say, for example, this obtuse angle is going to be about, let's go for, we'll say 120 degrees. Then the reflex angle around the other side, which is this part, will be 240 degrees. You can, of course, look at measuring these angles by using a protractor. I'll just show you, for example. So if we had now this one, let's put this in place. Let's say that goes to there, and you wanted to measure the size of the angle just here. So you wanted the size of this angle, you simply put the protractor on. The vertex just here goes in the center, and we read up 10, 20, 30, 40, 50. This angle looks to be about 55, let's see if I can write that, about 55 degrees. So that's all we wanted. If we wanted this angle right here, from here to here, and let's just put a line on there. So let's say we wanted the size of this angle. All we would do, assuming we hadn't just done the last one, this time we would read round the inside. 0, 10, 20, 30, 40, 50, 60, round, and it looks to be about 125 degrees. We'd expect it to be 125 degrees because 55 from 180 is 125 degrees. So that's what we have. They are basic angle types, and you will be expected to use a protractor to measure those. Let's now move on, and we will look at some basic angle facts. We looked at angles on a straight line and angles around a point on the last part. We're just going to spend a little more time doing that. These are basic angle facts that we should be comfortable with. So if we have a straight line, the angles on this straight line will sum to 180 degrees. So if I had, for example, this angle just here, and we said that this one was going to be 60 degrees, we said now that this one was going to be, I don't know, let's say 35 degrees, and we needed to find the value of this one, which is x. We know that x plus 35 plus 60 must be equal to 180 degrees. So all we would do is simply add these two together and take them from 180. So that is going to give me the following. If we subtract 95, x will be equal to, that will give me 85 degrees. So angles on a straight line sum, and if you're ever asked, you must use that terminology. You can't just say angles on a straight line are 180. They sum, they add to 180. Okay, let's look at another scenario. Let's say we've got a line like so, and something that looks like that. Then what we'll have is, let's go for something that does something like that, and then we will have this one, and we will have, let's just put this on, let's just leave it with this for now. So what we've got are the next things, which are angles around a point. If you do one complete turn or one revolution, it's 360 degrees. So what I'm going to do is put a little square there. I'm going to say that this value is going to be, now on here, we will have x, we will have this one is going to be x, and we will have now that this one is going to be y, and we will have now that AB is a straight line, and we will have this angle just here, and we'll say that this angle is going to be 50 degrees. We might be asked to find the value of x and y. So angles around a point equal 360 when added. Angles on a straight line equal 180 degrees when added. So if we're given this scenario, the first thing I would do is simply put now on here that this right angle here is going to be 90 degrees, as we got a little square. So if AB is a straight line, what we can say is that 90 plus the 50 plus the x will be equal to 180 degrees. So from this we can see now that x would be equal to 40 degrees. So if this is 40 degrees here, this one too is x, and that would be 40 degrees. So if AB is a straight line, we know that this angle right here must be 180 minus the 40, so that is going to be 140 degrees too. If we look at adding them up, 90 plus 40, that's 130, 180, then we'll have 220, 360. So angles around that point give us now 360 degrees when added. So let's look at this one just here. It says find the value of P in the diagram below. So all we've got now is an algebraic expression. We've got 1P plus 2P. So if we add those together, we know that 3P must be equal to 180 degrees, as angles on a straight line add to 180 degrees. 180 divided by 3 is going to give us P, so we can see now that P will be 60 degrees. So this one is 60 and this one is 120. If we look now at this one, it says the angles A, B, C and D are shown below. So we've got A, B, C, D, like so. So that's now around at a point. In part A, we're asked to write down which two angles are obtuse angles. So obtuse angles are greater than 90 but less than 180 degrees. Well, we can see now that the acute angles, the smaller ones, are A and C. So the obtuse ones are going to be B and D. Given that D and B are both over 100 degrees, find the maximum value of A plus C. We will assume these are given as integer whole numbers. So integer values. So if we have B, let's say B is going to be 101 and D is going to be 101. So the maximum value is when these are at their smallest. So if we add these two together, D and B would be 202. We know that angles around a point give us 360. So 360 minus 202, that's going to give us 158 degrees. So the maximum value of A plus C must be 158 degrees. I'm going to assume that B and D aren't 100.0000001. We will assume that being over 100 would mean 101. Explain using the diagram why the angles B and C sum to give more than 180 degrees. So B and C, if we had now 180 degrees, we would have a straight line. So I would make reference now to this being greater than a straight line in terms of the angle, or you can say that the complete angle is going to be a reflex angle. So some reference to if this was 180 degrees, then it would cut off here, or saying that B plus C is a reflex angle, therefore greater than 180 degrees. In the last part it says given angle A is 59 degrees, find the value of B plus C plus D. So all we need to do on this one is simply take the 59 from 360 degrees. 360 minus a 59 is going to give us 301 degrees. So nice and straightforward, nice and logical. In this one it says given AB is a straight line, find the size of each angle shown in the diagram below. So what we have then is the following. We've got now 90 degrees again, so similar to the one I've drawn. So we know that if this is a straight line, what we've got is y plus 2y, which is 3y must be equal to 90 degrees. We know that line is straight, angles on a straight line sum to 180 degrees, so y is going to be equal to 30 degrees. So this one is 30 degrees, 2y would be 60 degrees, 2y here is going to be 60 degrees, and we know that AB is a straight line, so this angle right here is just simply 60 from 180, which will give 120. do check that they add up to 360 degrees. Let's now move on and we will look at some angle facts. So what we're going to do is have angle facts, and we're going to have opposite angles, alternate angles, corresponding angles and co-interior angles. So I'm just going to draw up some lines here and we will just go ahead and start these like so. Let's get that straight, and that is going to be now. So all I'm doing is sets of parallel lines. So if I just put on now, these are parallel and we can show that they're parallel. Let's go ahead and just put these on. So let's just show they're parallel. So that's parallel, and that one is parallel with that one, and that one is parallel with that one. What I'm also going to do is add a transversal to each of these lines. A transversal is just a line that's cutting those two parallel lines. So let's start off now with the first one, and that is opposite angles. Opposite angles are equal. So if we've got these two straight lines here, this angle and this angle are the same size. So if this one is x, this one is x too. If we look at the other opposite angles, this one is going to be the same as this one, that would be y, and that would be y. What we should also recognise from there is x plus y would be equal to 180 degrees, angles on a straight line. And then 2x plus 2y would be equal to 360 degrees as the angles around a point. Okay, so that's opposite angles. Opposite angles are equal. Now what we're going to look at are alternate angles. Alternate angles used to be called, well, they've always been called, but you were used to be allowed to use the term Z angles. So if I have this angle just here, which I'm going to have as x, and this angle just here as x, we can say these are alternate angles. The reason we called them Z angles, if I just put this on, when we drew something like this, it looks like the letter Z. So we call these alternate angles like so. So these ones now are going to be x. I could put some more on here, and this is slightly harder to see. If that one is y, that one is y too. And you can see it looks like a Z, but backwards from there. So those are alternate angles. The next ones we're going to look at are corresponding angles. We used to be able to call these F angles in the exam, but now we must refer to them as corresponding angles. So what we're going to do is put these on. So that one and that one, for example, could be X. The x's are not, these x's aren't the same as these x's. I'm just doing individual diagrams each time. So the reason these were called F angles were as follows. If we go ahead and do this, if we look at that, that looks like the letter F. So these are corresponding angles or F angles. When we put this on just here, what we've got, this one, let's say that's Y, this one is Y2, as they are corresponding. So corresponding angles are equal. Let's now look at the last type, and that's co-interior angles. Co-interior angles sum to 180 degrees. We used to be able to call these C angles. So what I'll do is just put these on. So if this one is X and this one is Y, we can say now that X plus Y will be equal to 180 degrees. So we need to label these co-interior angles. We used to be able to call them C angles, but no longer. And the reason we could call them C angles is because they looked like a C. So that's the C like that, and that's what we'd have. So they're enclosed between the parallel lines. So Z, F, and C. Alternate, corresponding, and co-interior. So opposite angles are equal, alternate angles are equal, corresponding angles are equal, co-interior angles sum to 180 degrees. So this is a typical exam style question. It says find the sides of angle A and angle B. So what we've got, I'll just put these on, it's quite hard to see. This one is 120 degrees, so we've got 120 here, we've got B just here, and we've got A just here. It says you must give a reason for your answers. With this, there's a few different approaches. What you could do is say that these are alternate angles. So if we look now, we could say that B and 120 are alternate angles. As you can see, we've got the backwards Z. Alternatively, what you could have done is said that these are corresponding angles, so A and the 120 are equal as they're corresponding. So that is the F angle, the corresponding one. It doesn't matter which approach you take. What you could have done is something totally different and said that this is now a straight line, and we would have had angles on a straight line. So angles on a straight line sum to 180, so this would be 60 degrees. And then we could have said now, and I'll just put this in a different colour, that these two, the 60 and the B, are co-interior angles. So you could use any of these particular facts, but you must state which one you've used. So we know from this that whichever way round we go, B is going to be 120 degrees. You certainly don't have to get these in alphabetical order, so you might find B before you find A. At that point, all I would say is that A and B are opposite angles, so A would be 120 degrees too. So you must use the correct terminology: opposite, alternate, corresponding, or co-interior. In this one it says, mark on the diagram below two angles that are co-interior. So what I'm going to have is this one, co-interior are the C angles, and they're inside. So co-interior, inside. They're two that are co-interior. We could have had these blue ones, it doesn't matter. Those two would add to 180, as would these. So nice and straightforward. So those are angles in parallel lines. Let's now look at bearings. Bearings are basically angles, but it's a topic students really struggle with. So what I'm going to do is just start this off, and we're going to look at two towns. We're going to look at town A just here, and we're going to look at town B just here. What we're going to do is find the bearing of B from A and the bearing of A from B. Whenever you have a problem like this, all we do is start off with north lines. So that's a north line and that's a north line. So these two lines are pointing north and they are parallel. So if we put on here that this is the north line, this one is going to be parallel to this one. I then connect the 2 points, A to B. So what we'll do to begin with, and I'll just write this on, we're going to get the bearing of B, and this is the important bit, of B from A. When we hear the word from, that is where we measure. So all I'm going to do is get the protractor, and hopefully this will behave itself, and put now the centre like so. So what I'm going to do is measure the angle of B from A. We can see measuring around the inside, this gives us 45 degrees. So from north up to B, the line that B is on, that's 45 degrees. When we are measuring bearings, we must measure from north, we must measure clockwise, and our answer must be 3 figures. So as you can see, all I've done is taken it from the north line, I've measured north, from north, I've measured clockwise, and I'm going to give it what we call a 3-figure bearing. The angle was 45 degrees, so the bearing is 045 degrees. Of course, anything 100 or greater, you don't need to worry about putting that 0 in front of it. So the bearing of B from A is 045 degrees. What we're now going to do is the bearing of A, so of A from B. So this time we're starting at B. So what we're interested in now is the angle that goes round the outside, because we measure from north, we measure clockwise, and we give it now a 3-figure value. So before I was measuring from north clockwise to this line. What I need to do now is measure this angle right here. So what we're going to do is use the protractor. I know, hopefully, let's just spin this round. What I know is that angles on a straight line sum to 180 degrees. If you've got a protractor that is 360 degrees, this is a lot easier. So from this point round to here is 180, and then I can see it's an additional 45 degrees on, 180 plus now the 45 degrees is going to give me 225 degrees. So the bearing of A from B is 225 degrees. So that's using a protractor. What we can do is use angle facts. I'll do another example and we will have C and D. So I'll put C just here and I'll put D just here. So let's go ahead and put C and D. So if I put now a north line, so that's my north line at C, I'll have a north line at D, like so. And then I will connect the 2 points. So if we go ahead and connect the 2 points, it's something like so. So we might be given now the angle just here, or if you like, the bearing. Sometimes we will use angle facts instead of a protractor. So it will tell me without a protractor, find a certain value. So what we're going to do is put that this angle right here is going to be 120 degrees. The questions that might say, find the bearing of D from C. Of D from C is 120 degrees, which we would be given in the question. And it will say, without using a protractor, find the bearing of C from D. So what we now want is this angle right here round the outside. What we do is use angle facts. We've already seen in the previous section that co-interior angles sum to 180 degrees. These two lines are parallel. You can see this as a transversal. So this is going to give us now an angle of 60 degrees. The reason being those two equal to 180. So 180 minus 120 is 60. Therefore, this angle round here is simply 360 minus the 60, which is going to give us 300 degrees. So that's what we have. Now, if we look at this one we've just done, if I dropped a line down there, what you might spot now is that we have this angle and this angle. These are alternate or Z angles. So this angle is 45 degrees. We know that this one is going to be 180. So we could do it that way as well. 180 plus a 45 is 225, as we saw. So in some scenarios, you might be asked to use a protractor to measure and find the bearing. Alternatively, you might be asked to use angle facts. So in this one, question 7, it says measure the bearing of B from A. So of B from A. So all I'm going to do is go ahead and get this. We're going to spin this round. Hopefully this will behave itself. There we go. That looks okay. So if I put that just there, we're measuring now this angle just here. So on the inside, we got now, that looks to be about bang on 60 degrees. So this one just here, so that is going to be now 060 degrees. So that's the bearing of B from A. Of course, if we wanted now the bearing of A from B, we would find that one. And you could just add this now to the 180, or you could find this one and take it off. So that's going to be 240. We're not asked of that, but that is the bearing of A from B. So as you can see with these angle facts, it's a choice in which you have. And then part B, without using a protractor, calculate the bearing of C from D. Well, that's exactly the one we've just done. So that's what we have. So I'll do this the second way, the way that I did that just there. If you drop a line down here, then what we know is that this angle just here would be 122. So that one is going to be 180. So that in total is 300. So that's using the alternate or Z angle approach. Right, let's do this one. So town A and town B are shown below. We're asked to find the bearing of town A from town B. So all we do is put a north line at A, we put a north line at B. So we want the bearing of town A from B. So this one is slightly more challenging. I'll put that just there. And we can go ahead now and do that. These are the north lines. So that's north and that's north. So with this, if I get the protractor, remember, we want of A from B. So we're coming right the way round here. So you could use angle facts, or you could simply go ahead and measure it. So the way I'm going to do this is simply now turn this that way round. I'm going to put this in place like so. I know now that from this line here down to here is 180 degrees. So all I'm going to do is add this additional 10, 20, 30, 40 on. So let's move the protractor, that's what we want. So that bearing is going to be 180 plus the 40, so that is going to be 220 degrees. On the next part, it says given that half a centimetre is equal to 1.5 kilometres, find the distance from town A to town B to the nearest 100 metres. Simply put your ruler on it, go ahead, find the value, convert it up. I don't have a ruler to hand, so we won't do that one. Okay, let's have a look at these ones. So Fred walks, let's look at this. So Fred walks on here, what's he got? 4 kilometres east. So let's start him off just here. So he walks 4 kilometres east and then 9 kilometres west. How far from his starting point does he end and on what bearing? So a slightly different question here. So what he does, he walks 4 kilometres east and then he's going to walk 9 kilometres west. So if we look at this, what we're going to have is this is going to be 4. This is going to be 4 back, so that will be 5. So that's what he has. North, east, south, west. What we need to do now is work out his bearing. So if I just go ahead and put the north line here, what we've done is a 3/4 turn essentially. So if we look at the bearings, this would be now a 90 or 090. Then this would be 180. So this round here is going to be 270 degrees. Let's do the next one. I think the bottom one is exactly the same. So let's just do this one here. So the bearing of A from B is 126 degrees. Find the bearing of B from A. So let's just draw this up. So it looks something like this. So what we'll do is put on here. So the bearing of A from B, I'll put B just here. There's my north line. I put A just here. There's my north line. So this is going to be 126 degrees. So all we're going to do now is find the bearing of B from A. That's this one round here. So you could work out this one and subtract it from 360. So that would be 54. So if we have 54, remember these are co-interior angles, they equal to 180. So all we'd have now is 360 minus the 54, which is going to give 306 degrees. So that's that bearing there. Alternatively, what you could have done is just use the alternate angles. This one is 126, this one is 180, add the two together, you get 306. So these are bearings, or 3-figure bearings. Must measure from north, must measure clockwise, must give them 3 figures. Okay, we're now moving on to the interior and exterior. In fact, I think we've missed one. There we go, that's what I wanted. The types of triangle, we'll look at types of triangle first. This is another thing that could have been anywhere in this particular unit. What we'll start off with is a right angle triangle. Right angle triangle, as you can probably imagine, will have a right angle in it. So we'll always see a right angle triangle and it will have that little square in to show that that's a 90-degree angle. So if this is 90 degrees, this one and this one will also add or sum to 90 degrees. The angles in a triangle sum to 180 degrees. So this one plus this one plus this one will always equal 180 degrees when added. The next type of triangle we're going to look at is an isosceles triangle. An isosceles triangle has two equal sides which have a little line on them and two equal angles. So if this is x, then this is x. If we now look at the next one is an equilateral triangle. With an equilateral triangle, each angle is the same size and each side is the same length. So these are all going to be the same length, and each of these angles will be 60 degrees. We know that the angles in a triangle sum to 180 degrees. 180 divided by 3 is 60. Finally, we've got a scalene triangle. A scalene triangle will have no side lengths the same. So that is an example of a scalene triangle. Again, the angles in here, all of these sum to 180 degrees. So let's look at a typical exam style question. An isosceles triangle has an angle of 35 degrees. State the possible values of the other two angles and sketch the triangles below. So let's just draw up an isosceles triangle, and I'll have one just here, and then I'll have one just here. So with an isosceles triangle, we know that two angles are the same and two side lengths are the same. So let's say now that the 35 degrees was here and it was the single angle. So what we know is that these two angles are simply going to be 180 minus the 35, and we need to halve our answer. So 180 minus 35 is going to give us 145. 145 divided by 2 means that each of these will be 72.5. So what's that? 72, 100, let's just do this. My maths is failing me at this stage. So 180 minus, what is it, 62 and a half? 72 and a half, that's fine. So 72 and a half and 72.5. So that's what we get. If we look at those, we need to split that. So this one's 35 and these two base angles are both 72 and a half. What we could have had though is that this one was 35. These two sides are going to be equal. Therefore the other base angle would be 35. So if we do 35 plus 35, that gives me 70. So this angle here is just 180 minus the 70. So that's going to give us 110. So these are the two possible triangles. What we should know about an isosceles now are two angles are the same, two side lengths are the same. Okay, let's do a trickier exam style question. It says, draw a point C such that triangle ABC is one isosceles, two right angled and three scalene. So what we need then is an isosceles triangle using this line and one other point which will be C. So what I'm going to do, if I get this line like so, that is going to be the same length, and hopefully this will, well, it's not been brilliant, but it's given me some idea. So what I can do is put now the point C over here. So I've just created now an isosceles triangle, and if we put on here that this is going to be the point C, so I will show the examiner that this side length and this side length are the same. So triangle ABC is now isosceles. On the next one, we need a right angle triangle. So all I'm going to do is drop a perpendicular line down here. So perpendicular at right angles, and then connect this up, and we'll just put that this point is going to be the point C. So we can put that that point is a point C, and there is my right angle. On the next one, we need a scalene triangle. So if I go ahead and do something like that, that is an example of a scalene triangle. So if we just put C on here, all three sides are different lengths and all of the angles are different. So those are types of triangles. We're going to move this on now and look at the interior and exterior angles of polygons. I'm going to split this into two. We'll start with any polygon and then we will look at regular polygons. It's important to understand that the sum of the exterior angles of all polygons will be 360 degrees. When we're talking about the exterior angle, what we've got is something like this. So the interior angle, if I pop this on, so this one is the exterior and this is the interior. Interior and exterior angles are on a straight line and sum to 180 degrees. For all polygons, multi-sided shapes, the sum of the exterior angles is 360 degrees. We saw in the last video, and it doesn't matter whether these are equilateral or regular, we'll look at those shortly, we have 180 degrees as the sum of the interior angles of a triangle. Every time I add a side length, so this is 3, this is 4, what we can do is increase the number of triangles by 1. So in a square, I've got 2 triangles. So I know that this is 180 and this is 180. So that gives me the interior angles sum to 360 degrees. And that's true for any quadrilateral. So just because that's regular and it's a square and they're all 90 degrees and you've got 4 of them, that will work for any quadrilateral. So if I've got this quadrilateral now, these will still sum the interior angles to 360 degrees. So if I put that on there, that one, that one, that one, and that one sum to 360. If we now look at the pentagon is a 5-sided shape. This time I can get from one of the corners or the vertices, I can fit 3 triangles in. So we've got 180, we've got 180, and we've got 180, and that's going to give me a sum of 540 degrees. If I do the same now on the hexagon is a 6-sided shape, from one of the vertices, it doesn't matter which, we can get now 4 triangles. So again, if I put this on, let's put this on, this is going to be 180, 180, 180, and 180. So we can say now that the sum is going to be 720 degrees. Each time we add a side, we add 180 degrees to the sum of the interior angles. So this one is going to be 900 degrees, this one is going to be 1080 degrees, and so on and so forth. There is a formula for the sum, the total of the interior angles, and that is n minus 2, where n is the number of sides times by 180. All this is saying is take 2 off the number of sides and times it by 180. So 3 sides minus 2 is 180. 4 sides, 4 minus 2 is 2, 2 times 180, 360. 5 minus 2 is 3, 3 times 180 is 540. So that is now finding the sum of the interior angles. What we're going to do now is look at regular polygons, and we're going to look at finding an interior and an exterior angle. So we could go ahead and use this particular approach here. What I'm going to do instead though is just build this up. To find the size of each exterior angle of a regular polygon, we simply do 360 divided by the number of sides. As I introduced a moment ago, the exterior angles will always sum in any polygon to 360 degrees. So if I wanted the size of this angle here, all I do is 360 divided by the number of sides. 360 divided by 3 is 120. That is the exterior angle. This is the interior angles, and angles on a straight line sum to 180, so this will be 60 degrees. 180 minus 120 is 60. Well, we knew this anyway because an equilateral triangle is regular. So this one is 60, this one is going to be 60, so we can now say that each interior angle is 60, or the sum is 3 lots of 60, which is 180. If I now get up a regular, and this will be regular, that is a regular pentagon. So this has got 5 sides. So to find each exterior angle, the size of that, I simply now take 360 and divide this by 5. 360 divided by 5 gives 72 degrees. Angles on a straight line sum to 180. So 180 minus 72, that is 108. So if that's 108, all of the others are. And of course, if you wanted to find the sum, then all we would do is do 5 lots of 108, which would give 540. So that's, and of course, if these are regular and you've used this approach, you just divide this number by the number of the angles in there to get one interior one. let's do one more. We'll steal one of these. So if we look at this, this is a decagon. So a decagon, and I'll put the exterior angle here. So that is the exterior angle. Decagon has got 10 sides. So we would do 360. So 360 divided by 10. 360 divided by 10 is 36. That's the exterior angle. So the interior angle, the size of one interior angle, will be 144. 180 minus 36 is 144. So if you wanted to work out the sum, you just have 10 lots of 144, which is 1440. Of course, if we added now 360 to this one, that's what we'd get. So 180 to that one, and then you'll see that we would have got 1440. Right, explain why angle Z in the picture below is 80 degrees. Okay, this would be a 5-mark question, and we'll start this off and we'll look at what we've got. The first thing I'm going to look at just here is this isosceles triangle. I know it's isosceles because I've got now the side lengths just here with the little arrows on. So straight away, I know that the base angles are going to be 70 degrees each. 70 plus 70 is 140, so this would be 40 degrees. You must state this in your working. You must say isosceles triangle, base angles are equal, this is 70 degrees, therefore this one is 140. What we've also got here is a quadrilateral. This quadrilateral here, and I'll just put that there, we've got now a 4-sided shape. We've already established that the sum of the interior angles of any quadrilateral will be 360 degrees. So if I just put this here, we can say on here the following. This one is going to be 90 as we can see the right angle. Angles on a straight line sum to 180. So if this is 70, this is 110. We can find x by saying that x plus 110 plus 90 plus 100 will be equal to 360. So that's going to give me on here that x is going to be equal to 60 degrees. So this one is 60, and then all we would need to say is that the 40 plus x plus the z would be equal to 180 because angles on a straight line sum to 180 degrees. That would go there. So we can see on here we've got the value of x. So we can say that 40 plus 60 plus z is equal to 180 degrees. So 100 plus z is equal to 180 degrees. So z will be equal to 80 degrees as required. So all you need to do is make reference. I didn't write down exactly what I should have done because it would have taken me ages, but you must reference isosceles triangle. So we know the base angle the same. We must reference here this quadrilateral. So interior and exterior angles of polygons. Okay, let's now look at parallel and perpendicular lines. We've already discussed these to some extent, but we'll do a little bit more on here. So what we've got here says the lines A, B and C are shown below. So there's A, there's B and there's C. We're asked to complete the sentence. Line B is something to line A and something to line C. If we have parallel lines will always have the same distance between them. So they will never meet, and we can denote those or put this on to show that. So those are parallel. Perpendicular lines have a 90-degree right angle. So those two lines are perpendicular. This line is perpendicular to this one. And we could, if we want, if they intersect, so if they cross, we could put that that is going to be the right angle. So line B is perpendicular. So perpendicular, and we'll just write this in, perpendicular to line A, and it's going to be parallel. So parallel to line C. So parallel and perpendicular lines. Okay, let's look at an exam style question. It says, mark the points P22 and Q64 on the grid below. So P is 22, that's going to be just there. and we've got now Q 6, 4, 6, 4. That's going to be Q, and Q is going to be just there. What we need to do is write down the midpoint of the line PQ. So if we look at the line PQ, the line PQ does that, and we can see either visually, or we could use the midpoint formula which we met. The midpoint is just here, and if I just put that is M, the midpoint, that has the coordinates 4, 3. If you wanted to do it, you could add the x's together and divide by 2. So 2 plus 6 gives us 8. 8 divided by 2 is 4. 2 plus 4 is 6. 6 divided by 2 is 3. You may see that more visually just by drawing a line between them. We're now asked to draw a line perpendicular to the line PQ. So here's the line PQ that passes through the midpoint of the line PQ. So what we're going to do is draw a perpendicular line. I've got the ruler here because I certainly think when you're doing this, if you use your ruler, and let's just change this over, there we go, that's what we want. What I would do when you're drawing a perpendicular line is take your ruler and put one of the lines bang on. So where you can see that 3 measure just here, you can see that this line is directly over the other one. So all I'm going to do is go ahead, put that there, that looks pretty good, and then draw a line that is perpendicular to the line PQ that goes through the middle. So that will look something like that. That's not horrendous. It's probably not spot on, but certainly if you were doing it in an exam, it would be. So let's put that back. Didn't want to lift that bit. We wanted to lift the ruler, didn't we? So let's lift the ruler that way. There we go. So what we've now got on the next part, it says the point R is the point such that the triangle PQR is a right angle triangle. Mark on the grid one point where R could be. So this is nice and straightforward. All we need to do is think of a right angle triangle. So PQR is a right angle triangle. So it could be there. We could put it just there. And we could mark the point at 2, 4. We could choose something else. Let's say, for example, we wanted to put it over here. We could put it over here. And we could put it at 6, 2. So I'm going to put it there. 6, 2 would be perfectly fine. And this is going to be the point R. So the point R is just there, and we've got now the point 6, 2. So you did have a choice with that one. So that's what we would do. So those are parallel and perpendicular lines. On the higher course, you will be expected to find the equation of those, but in this particular course, it's done purely by a visual method rather than algebraic, or in terms of using geometry rather than algebra. Okay, let's now look at angle and line bisectors. This means that we cut an angle in half. So if I had this angle just here, what we would do is look to cut this angle in half. If I had a line, what we would do is look to cut the line in half, and we would have what we call a perpendicular bisector. I'm going to have a go at these with the compass I've got. Hopefully it will be a good enough demonstration. So what I'm going to do now, I'll just move this out of the way. I'm going to draw an angle. This might, hopefully this might work. It might not, and if it doesn't, I apologise in advance. So what we'd have is this angle. We choose the angle, and we're going to now, let's just kill that. Don't need this. What we do is put the point of the compass at the vertex of the angle. What we then do is swing an arc. Let's just change that to blue. When I say swing an arc, what we do is open up the compass like so, and we simply now draw, and hopefully this will do it for me, we draw an arc just here without taking the compass off the spot just on the vertex. We draw another one. What I now do is pick the compass up, so hopefully this will move. Will it allow me to move it? Okay, it should allow me to move it. Hopefully it'll allow me to move it. Is it going to? I want it to. There we go. I knew it would. We then, keeping the compass the same width apart, we place the spike or the pointy bit of the compass here, and we go ahead and swing now another arc. So if I swing an arc here, I then take this off and place it on the other point that we've just made, and we swing an arc again. So if I swing an arc, where these two meet is the point that we need to draw a line from. And I've just moved, let's see if I can move that. Is that going to move? Yeah, there we go. All I need to do now is simply go ahead and draw a line from the vertex through that point here. We certainly do not rub out our construction lines. So don't get rid of these, just leave them. We have this angle here and this angle here. If this one was X, so this one too would be X. Whatever the size of this angle is what that one is. And we call that an angle bisector, and it cuts it in half. What we're now going to do is look at the perpendicular bisector of a line segment. So what I'm going to do is draw a line, and let's go for that. So my line's going to start here, and we're going to cut this line in half. I've got a feeling this is going to be not a brilliant demonstration given the lack of flexibility I've got with this thing. What we do is put the compass on one end of the line, right on that point. We open, there we go, we open the compass up beyond halfway of the line. We then swing the arc at the top, and we swing the arc at the bottom. Without changing the compass, we move it to the other end of the line. So we come to this end of the line. Now, clearly you're going to turn your compass the other way round. I don't have that luxury on this one, so your compass would be pointing this way. And all you need to do, and I'll just come back round this way, is swing that arc like so. So that's what we have. As you can probably see, if we were the other way round, I used to think that I could flip this. I think something has gone wrong. So that's all we do. We draw a line now through the points. Let's just put that on. It's not going to be absolutely spot on this, but it gives us some idea. There we go. What this does is creates what we call a perpendicular bisector of the line. So this line is perpendicular, and this length right here is going to be the same as this length right here. That's what I've shown by these two marks to show that those two side lengths are the same. So if we were to measure now, and I'll start this on 1, that looks to be about 2.7. If I measure now on here from, let's go on, we'll start it just there, that looks to be 2.7. So we can see that that creates the perpendicular bisector of a line segment. I wouldn't want this over here because I just would have turned the compass around if I could figure out how. You will obviously just switch it around. But whatever you do, don't alter the compass. Just leave it as it is. And leave your construction marks on. You must show that you've done these arcs. If not, it may be assumed that you've just used a ruler instead of the compass. Let's now move on to look at loci and regions. The locus of points is simply something that satisfies a rule. So if I drew a circle now, and we had this circle, and this had a radius now, let's put a radius on here, and this radius was, let's say this radius, that looks about 2 centimetres, let's call this 2 centimetres. All of the points on the circumference of this circle are exactly 2 centimetres from the centre. All of the points outside the circle are more than 2 centimetres from the centre, and all of the points inside the circle are less. So what we can say is that these are the locus of points, and I'll shade it. The blue ones are now the locus of points that are more than 2 centimetres, and we'll just call this A. So the blue bit of the points more than 2 centimetres from A, and then we will have the green one. The green points are those that are less than 2 centimetres away from A, and on the line itself are the points exactly 2 centimetres away. And we just simply call those the locus of points. So what I'll do, hopefully this will give we'll try this one. So let's put this point here. Let's put this point on here. Is it going to let me do it? There we go. So let's call that point just here X. So if I wanted to do the locus of points that are going to be now more than 2 centimetres away, all I would do is put my ruler here and open that up 2 centimetres. Then I would simply draw a circle like so, and now I've got the locus of points, and if I wanted the locus of points now that were greater than 2 centimetres from X, I would shade outside. Exactly 2 centimetres from X is on the circle, and less than 2 centimetres from X is inside the circle. Let's just expand that on a little. Let's just move that. Let's see what we want to do. In fact, okay, I think, there we go, that looks okay. What I'm now going to do is look at the points that are going to be more than 2 centimetres from X, but less than 3 centimetres from X. So the points that are more than 2 centimetres from X, but less than 3, are the inside of this polo or donut. So is it going to allow me? No, it won't allow me to scribble on there. Allow me just there. Oh, that's okay. So they're all the points that are more than 2, but less than 3 centimetres from X. So we call that now the locus of points. What we will look at here, and I'll just extend this on a bit. If this one is A, there we go. If that one is A, and this one is B, what we've got, if we do a perpendicular bisector, these are the points closer to B, this side, and these are the points closer to A, this side. So the locus of points closer to A than B, with this one being A, it will hopefully, there we go. Oh, I don't know what that's doing. And this one being B, if you do a perpendicular bisector, you can get the points closer. So this side, closer to A, and this side are closer to B. So do look out for that wording. So it's either going to be a circle or a perpendicular bisector. So it says write down what the shaded area shown below represents. So I'll just put this on. This is A, and this is 5 kilometres. This is going to be B, and that's going to be 3 kilometres. So what have we got? Well, if we look at these two circles, and I'll just shade them in. So in this, we've got a solid line around the outside. So we can include the 5 kilometres. If it's a dashed line or a broken line, you could say that it's strictly less than 5. So all of these points are equal to or less than 5 kilometres from A. So hope that's just going outside. But so everything yellow is equal to or less than 5 kilometres from A. Everything now that is green is equal to or less than 3 kilometres from B. So this dark bit just here are the points that are equal to or less than 5 kilometres from A and equal to or less than 3 kilometres from B. So that's the region, and we would call it a region that satisfies both. So if I just look at that, they're all the points or the locus of points, and that would just give me this part just here. So nice and straightforward, nice and logical. So that's that. We've just done one similar to this. Mark all of the points more than 1 kilometre from point X, but no more than 2 kilometres. So we would just open that compass up. We would do a 1 centimetre radius circle. I'll just do it on here. And then we would do a 2 centimetre radius circle. So we would get what looks like a donut or a polo. But you have to obviously use your compass of that and make it clear. So all we'd have is this part just in here. So let's just do that. That's what it looked like. So do make sure it's accurate. I'm not going to try and do it again with the compass. I think I'm riding my luck a little bit. So that bit's going to be just there. Obviously you've got this bit here, but the highlighter's not gone over that. So let's just put that in there as well. Slightly different colour, but hopefully you'll see. So that is now the locus of points. Let's move on, and we're going to now look at the 4 transformations. When we're talking about transformations, we're either talking about translations, which means to move a shape, rotation, which means to turn a shape, reflection, which means to mirror the shape, or enlargement, which means to make the shape a different size, whether that be bigger or smaller. So let's look at this in action. We're asked to plot the points 1, 1, 2, 1, and 1, 2, and connect the dots to make a polygon. So 1, 1, we've got 2, 1, which is just there, and we've got 1, 2, which is just there. So what we're going to have is a little triangle on here, and let's see if I can grab that up. That'll look something like that. So that's all I needed to do. That's what it looks like, and we need to now label the shape A. Is that colour okay? In fact, let's just change this. So we'll change it so it's easier to see. So let's just have it as red. There we go. That is now shape A. So if we put on here, now this is going to be shape A. What we're asked to do initially is translate shape A by the vector given below and label the shape B. Translate means to move. The easiest way to think about this is if you're playing chess or drafts. You translate the pieces. You can move them around the board. What we do is have a vector. I'm going to write a few vectors out. If we've got 2, 1, if we've got now -1, 3, if we've got, for example, 4, -1, if we've got -6, -3, if we've got 0, 1, and we've got now 4, 0. The top number tells us whether we move left or right. If it's right, it's going to be positive. If it's negative, it will be left, or left is negative. The bottom number tells us to move up or down. If it's positive, it moves up. If it's negative, it's going to move down. So negative is going to move down. So if we look at this one, this tells me to go right by 2 and up by 1. This tells me to go left by 1 and up by 3. Right by 4 and down by 1. Left by 6 and down by 3. No movement to the left or right or horizontally, but 1 up. 4 to the right and no vertical movement. So all we're doing is moving this one by 1, 2. You can think of just saying, well, I'll go across 1 and up 1, 2 and redraw it there. Alternatively, you can take a point. If we move this point 1 and then up 2, we redraw it there and draw the shape. It's entirely up to you on how you want to see that. So if I do that now, all I'm going to do is right by 1 and up by 2, and the shape goes here, and we can label that shape B. I'm getting frustrated when it keeps replicating me. I'll think why I'm doing it. I think it's because I'm holding on too long, but it's quite annoying. So that's shape B. We're now going to rotate A 180 degrees clockwise around the origin, 0, 0, and label it C. When you're given a rotation, you will use tracing paper. The 3 pieces of information you need are the centre of rotation, the direction of rotation, and the angle of rotation. So I'm now going to draw a piece of tracing paper, and your piece of tracing paper will look something like this. What I do is put this over the top. I'm now going to simply draw over the top of the shape. So over the top on your tracing paper, draw the shape perfectly. Then put a north line on the tracing paper like so. What I now do is put my pencil in the centre, that's 0, 0. Hopefully this is going to work, and what I'm going to do is just go ahead and group these, and I'm hoping now if I group them, what we do is keep our pencil on the centre and just rotate the paper. We're doing 180 degrees clockwise. 180 clockwise is the same as 180 anti-clockwise. So if I turn the paper now, this is 90 degrees clockwise. So I've rotated it about the centre. So it's pointing now to the right, or it's pointing east. That is a quarter turn. 90 degrees is a quarter turn. Half turn is 180 degrees, and the arrow will point downwards, it will point south, or at 6 o'clock on the clock. If I wanted 270 clockwise, we would do 3/4 of a turn. The arrow would point at 9 o'clock, or, if you like, west. So back where we started. So we want it 180 degrees, and it's going to end up just there. So if I let's just move this out of the way, and in fact, let's put that back. I think I can remember where that is, and then we will turn this. Let's see if there we go. So that's where I want it, and then we will just ungroup this at some point. So what did that look like? That looked like this, and that's what we'd have. We'd have that just there. So that's that. Obviously, you won't leave your tracing paper on here. I'm just going to leave it. So that one is going to be shape. This is going to be shape C. We now need to go ahead and we need, on the next bit, to enlarge shape A by a scale factor of 2 and label it D. When we've got a scale factor of 2, we multiply each side length by 2. What we don't do is add 2 to each of the side lengths. So all I'm going to do is make this twice as big. So if this side length is going to be 1, our D will be 2. This is going to be 1, D will be 2. So that is D. In this particular unit, we're not given a centre of enlargement, so I've just put it like so. If you had a scale factor of 3, you'd make each side length 3 times as big. If you had a scale factor enlargement of 4, you'd make each side 4 times as big. You're not adding 4, you're multiplying. So you can see now that is an enlargement. When we've got an enlargement in this particular unit, we will only be given a scale factor. We need now to reflect A in the x-axis and label it shape E. The x-axis is this line here, which is often known as the line y is equal to 0, as all of the y coordinates on here are 0. So what we've got to do is redraw this. When you look in a mirror, if you're 1 unit away, you will appear 1 unit away in the mirror. So what we'll have is something that looks like this. So this line will mirror here, this one will mirror here, and this one will mirror here. Whatever you do, don't get that the wrong way round. So this one is going to be shape E. Let's just look at a few lines we might be asked to reflect it in. If I was asked to reflect it in the y-axis, this is the line x is equal to 0. So in that particular case, what I would do is go ahead and I would put it, that's a distance of 1, that would be just here. So that's a reflection in the y-axis of the line x is equal to 0. If I reflected it in the line x is equal to 2, this is the line x is equal to 2, as all of the coordinates on there, the x coordinates will be 2. So that would look something like so. If I was asked to reflect this in the line, for example, y is equal to 3, this is the line y is equal to 3, and I would simply go ahead, this is getting a bit congested, I would put it up here, and that would be just there. In the algebra video, we looked at horizontal and vertical lines. So those are your 4 transformations. Translation means to move, rotate means to turn, enlarge means to make it larger or smaller. If we have a half scale factor, that means you make it half as big or twice as small. And then a reflection. And with the reflection, you will be given now the equation of the line. One more just to consider is the line y is equal to x. That is the line y is equal to x. And if we were asked to reflect it in this line, the x coordinates become the y coordinates and the y coordinates become the x coordinates for the new shape. So if you're struggling, just swap the x's and the y's around and redraw it, or you can use your tracing paper and flip it across the mirror line. So that is carrying out transformations. We might be asked to do a combination of transformations. I say we might, depending, you may be. So it says shape A is shown in the diagram below. So here's shape A, so it's a little Tetris block. Harry performs 2 transformations on shape A. He translates it by the vector 1, negative 1, followed by reflecting the shape in the line x is equal to 0. We're asked to show the final place of a shape and label the shape B. So what we'll do is start off with this vector. So if we look at this vector, this is 1, negative 1. So we're going to move it right by 1 and down by 1. If I move that shape right by 1 and down by 1, it's going to sit just here. So that is the vector, and we've translated it like so. So 1, negative 1 is right 1, down 1. So that's the first thing he's done to it. He's now reflected this in the line x is equal to 0. This is the line x is equal to 0, 0, 0, 0, 1, 0, 2, 0, 3, and so on and so forth. So all we need to do is go ahead and reflect it in this line. We can see that this is a distance of 2 away. Whatever you do, don't put it here. It's going to start just here. It will be back to back as well. Often a common error is that students put it this way round, like so, as well. That's not correct. We need to go with it like so. It's being reflected, and that will look something like that. And then we will have this, and we can label this shape B. I'd be inclined to just get rid of this one just here, but that shows if we got the second part wrong, we've got the first part right. So I might even do dotted lines on that one, but that is B, and I've labelled it shape B. So that is carrying out a combined transformation. What we now may be asked to do is name a transformation. So we'll have a transformation that has been carried out, and we might have to name that. We must be 100% clear. If we're saying it's a translation, we must give the vector. If it's moved, it's a translation and you give the vector. You can't just say moved across. You must say it's been translated, then give the vector. If you're talking about a rotation, you need to state the centre of rotation, the direction of rotation, and the angle of rotation. You can't just say it's been spun. If you're talking about a reflection, you must say it's been reflected in the line x is equal to, y is equal to, or the x-axis or the y-axis. So you must say it's a reflection, and you must give the equation of the line. If it's an enlargement, you must state the scale factor. Again, we don't need to state the point or the centre of enlargement. So in question 4, it says state fully the single transformation that maps shape A to shape E. So here's shape A and here is shape E. To me, that looks like a reflection. So I would state it's a reflection, and it's a reflection in the line y is equal to 4. So the transformation, it's a single transformation that takes shape E, shape A to shape E is going to be a reflection in the line y is equal to 4. You may spot that some of these could be rotations. If you're hunting for a rotation, use your tracing paper, draw it, and look to rotate it about certain points, and it's a bit of trial and error. Shape A to shape D. Well, that is going to be a reflection in the line x is equal to 3. Reflection, line x is equal to 3. If we now look at shape A to F, what we could do with this are two different ones. I think the easiest one is a translation. Translation by the vector 1, negative 1. We could have said, though, that this is a reflection, and that is going to be a reflection in the line y is equal to x. I'd be less inclined, though, to go for that in terms of the stating that as a transformation. I would say that it's a translation. In terms of let's just go ahead and do this. In terms of doing any form of rotation, for example, if you wanted to look at A to B and you wanted to say to yourself, is A to B a rotation? If you get your tracing paper again and just go over the top of that, what you could do is look for the centre of rotation. So if you thought it was just here, and let's just go ahead and group these. So let's do that. and you thought, I think I can spot a rotation, let's just group, then what you could do is check that out. I haven't grouped that one, have I? So let's, right, why is that not moving? But essentially what you would do, I don't know why, right, there we go, let's see if I can group that now. I don't think it picked it up, so group all of that. So if we rotated it now, and you can see straight away that wouldn't be the centre of rotation. So if you wanted to check what it could be, and you wanted to, if we put that back on there, so let's do that. You can try these points out. So with that one, let's put it there, and we're going to have to group all of this. Let's group that. So if we group, so just pop this on, and you can do this by trial and error. So there you can see now that from A to B, it's going to be a rotation of 90 degrees anti-clockwise about the point 0, 1. Or if you wanted, you can have 270 degrees clockwise. 90 degrees anti-clockwise is 270 clockwise. So all I've done is put my tracing paper over. You can see the first one I did was incorrect. The second one is correct. So that is naming the transformations. You must be clear in what you're doing. Okay, let's move on. What we're now going to do is look at line symmetry and rotational symmetry. Let's start with line symmetry. If you think about a mirror line, if we had a mirror and placed it on a shape, how many times would it look like itself? A nice place to start is the alphabet, and I've put here depends on the font. They won't be that cruel. If we're looking for mirror lines, let's take now the letter A. We know that the letter A would have a mirror line down the middle, so it looks the same on either side. B would have one here, possibly. It might not, but this side might look like this one. C would have a mirror line just there. D would have a mirror line just here. We would have E having a mirror line here. Now F wouldn't. So we can say A has one line of symmetry, B has one line of symmetry, C has one line of symmetry, D has one line of symmetry, E does. F has no lines of symmetry. G will have no lines of symmetry. Depending on how the H is done, H could have two lines of symmetry, a horizontal and a vertical one. I, again, depending on how it's done, will have a horizontal and a vertical line of symmetry. So these have two. This will have none. Depending on the way this is drawn, I would debate that. That will have no lines of symmetry. No lines of symmetry. M will have one line of symmetry. If we look at N now, N is going to have no lines of symmetry. Depending on how this is drawn, it could have, if it was a straight circle, it would have an infinite number of mirror lines. But depending on the font, you could say that's got two. P wouldn't have any. We've got now on here, Q wouldn't have any. R wouldn't have any. S isn't going to have any. T is going to have one, like so. U will have one. V is going to have one. W is going to have one. Again, depending on how X is drawn, it might have two lines of symmetry. Y would have one line of symmetry, and Z is going to have no lines of symmetry. So that's what we talk about when we're talking about line symmetry. It's mirror lines. What we're now going to look at is rotational symmetry. So if I go ahead and get another letter, and we will choose H, and I will now make this a nice font, so one that's going to be pretty consistent. Hopefully, let's choose that one, and let's make this, let's make it red. So what I'll do now is look at the rotational symmetry. If we have now a shape and we simply, and let's just get our tracing paper again, let's put our tracing paper like so. And now if I just group these together, what I'm going to do is put a center spot just here. So if I started now with my tracing paper facing north, and I completed one full turn, let's put that back, we certainly don't want to do that. There we go, let's group this together. So we need to now group. If I rotated this about its centre, is H going to go with it, or is H not included? Right, okay, that's what I need to do. So if I rotated this 100, okay, it's not going to do what I want it to rotate about that point. If we turn this right way around, how many times is it going to look like itself before it returns? The answer is going to be twice. So it will have a rotational symmetry order of 2. So when it gets down the bottom, the H will look like itself again. So turning it around, you will have a rotational order of 2. Yet if I took a letter like G, for example, if we rotated it 360 degrees about its centre, it would have no rotational symmetry because it wouldn't look like itself again. For all regular shapes, the rotational symmetry will be the number of sides it has. The same goes for line symmetry. So if we had now, let's get a regular pentagon. So if we rotated this, we would have now a rotational symmetry of 5, and we would also have now a line symmetry of 5. So through all of the vertices now we can draw these mirror lines, and they will look something like this. So we can see now that that gives it 5 lines of symmetry. Often students say, well, there are 10. Well, it looks like there are 10 parts to those. So let's just I don't like that there. Let's just get rid of that. So you can see now 5-sided shape, if it's regular, when you rotate it, it'll look like itself 5 times. And also it's got 5 lines of symmetry. If you put a pattern on it though, so for example, if we had a square has a rotational order of 4. But if I just drew, for example, a little X here, the rotation is 0. If I put an X, an identical X in the same place here, the rotation order would go to 2. So it's all it's often about the thing, but in the pattern. But in terms of regular shapes, the rotational symmetry and the line symmetry will be the number of sides it has. It says draw 3 different letters that have rotational symmetry of 2 and a line symmetry of 2. So we can see on here now that I can choose these from here. So we've got 3 letters. H has got line symmetry 2 and rotational order of 2. I will have line symmetry of 2 and rotation of 2. And then we could say now that X has a line symmetry of 2 and a rotational order of 2. So this has a line symmetry of 1 but no rotational order. This has a line symmetry of 1 but no rotational order. It won't look like itself. Okay, so it says on here, study the regular shapes below. We don't need that at all. Name each shape. So these are regular, so we're told they're regular. This is a regular hexagon, 6-sided shape, and a regular pentagon, 5-sided shape. State the rotational order of line symmetry of each shape. So this will be 6 because it's regular and it has 6 sides. This will be 5 as it's regular and it has 5 sides. Show that one of the shapes tessellates and the other doesn't. This is quite hard to show on here, and I'll explain this now. We didn't look too much in depth at when we were looking at tessellating, but if we have now just here these interior angles, what we've got now is 108, and this one is going to be, so this is going to be 100. What's this 6-sided shape? So that's going to be 120. If these are going to tessellate, the interior angles must be a factor of 360 degrees. So this won't tessellate, it won't fit together because they need to fit around a point. If you try to tessellate, have we got, there we go. So let's see if we can replicate this. I don't think that's horrendously bad. Let's go, oh, right, okay, so that's what we need to do. So let's get rid of this. If I pick this up here, that looks pretty good actually. If we copy that and get another one, hopefully that's somewhere just here. No, it's just there. Okay, I can't see it because it's black. No, okay, there it is. Is it? Okay, so it's not copying. But basically what we could do is this, and they would fit together. So when you think about tessellating, I don't know if they're still popular, but certainly in the 1980s, you had lots of floor tiles that look like this. So we can see that these fit together with no gaps. Yet we couldn't do that with the, you can do it with a hexagon because the interior angle is 120. You can't do it with the pentagon because it's 108. So that's part. Explain what is meant by regular. Same length of each side, so the same interior angle. Okay, draw a shape with a rotational order symmetry of 2 and B a shape with line symmetry 4. So rotational order of 2. Best one for that I think is a rectangle. A rectangle that isn't a square. And then one with line symmetry of 4, nice one for that would be a square. So line symmetry of a square we would have is going to be 4. So that's what we'd have. That's our line symmetry and rotation order. If we started there, that would look the same at the bottom and then we would get back round the other side. So that is symmetry. Let's now look at plans and elevations. The idea of plans and elevations is that we take a 3D drawing and make it into a 2D drawing. The plan view is the bird's eye view. So what would we see if we were on top of the shape? Often when you think of a house, and here's an example of a house, this is a house. This is what we call the plan view. So you would see this if you were in a plane looking down directly. You wouldn't see a 3D shape. You would see a 2D shape and it looks something like that. This one just here, this is what we call the front or the side elevation. We'll be told which one we have. So if this is a front elevation, that's what we'd see from the front. And this is a side elevation, what we'd see from the side. We won't see any slant on that roof. It will just be 2 rectangles. So let's go ahead now and do one of these. So this is the front elevation. So I will say now that this is the side elevation and the plan view will be from the top. So let's go ahead and use the square paper to draw this. So let's start off now with the front elevation. What I'm going to see now is this, what looks like a Tetris block. It will be 3 long and it will be now, you can say 2 high or 1 and 1 just here. And it will look something like this. And I'm going to put on now the blocks to show. So we've got all of these blocks and that looks something like that. So this now is the front elevation and I would label that up. So if I just put here, this is going to be the front elevation. Then the side elevation, all we would see is 2 blocks. So here, if I looked at it dead straight on, we would have now these 2 blocks and it would look something like so. That line should be straight at the bottom and then it looks like that. And we can say now that this is going to be the side elevation. So let's just straighten that one up. I don't like that like that. That looks better. Hopefully that's better. There we go. Then we want the plan view. What would we see if we were a bird with a bird's eye view? We would see now looking down, we would simply see a block. We would see now the block is going to be 3 long. And on here we can see that this one is not got a line on it. So all we would see is this and we would see that like so. So we would see the top block. We can't tell that this is higher than this one. And we would simply write now that this is going to be the plan view. So there we go. Let's move that out of the way. And that's what we'd have. So the reason I've taken that away is such that you can see it. Let's just put my other line on the side. I need one more line on there, don't I? So you can see now that that should just have that. So that is drawing now the front elevation, the side elevation, and the plan view. And these are called plans and elevations. You're taking now a 3D shape and you're drawing a 2D shape to represent that. Okay, let's move on and we will now look at metric units. So when we're talking about metric units, for length it's millimeters, centimeters, meters and kilometers. For mass or weight, it's going to be grams, kilograms and tons. and for volume, generally speaking, millilitres, centilitres and litres. So let's go ahead and just define a couple of obvious ones. In 1 metre, there are 100 centimetres. In 1 kilometre, there are 1,000 metres. Kilo means 1,000. So kilogram is 1,000 grams. Kilowatt is 1,000 watts. So in terms of mass, in terms of grams to kilograms, as we've just looked, it's going to be 1,000 grams in a kilogram. Millilitres to litres, we're going to have 1,000 millilitres is 1 litre. In the same way, 1,000 millimetres is 1 metre. So let's go ahead and look at a typical type of question we might be asked. So it says, convert in part A 300 millilitres into litres. So all we need to do is divide this now to get our value, and we know there are 1,000 millilitres in a litre. If we divide this now by that quantity, then we can write this in litres. So 300 millilitres is going to be equal to 0.3 litres. Fred has a number of glasses that can hold 300 millilitres of water each. He fills 14 from a 6 litre tank. Find out how much water is left in the tank, giving your answer in millilitres. So let's see what we've got here. We've got 6 litres in the tank. So 6 litres is 6,000 millilitres. You can do this either way. You can use your answer to part A, or if you're more comfortable to work the other way, you can convert the other way. So what we've got is the following. We've got 14 times by 300. So if you want to do that on a calculator, you can do. If you're comfortable, you can do it. That would give us 4,200 millilitres. So 14 times by the 300. Let's type that in. There we go. 4,000. So this is 4,200 millilitres. So how much was left? Well, all we got to do is 6,000 minus 4,200. So that's going to give us 1,800 millilitres. If you wanted to work in litres, what we would have had is 14 times by 0.3. That is going to give me now on here, 14 times by 0.3 is 4.2. If we got 6 litres, 6 minus the 4.2 is going to give us 1.8 litres left. Therefore, if they need our answer in millilitres, we need to multiply this by 1,000. Let's look at this one. James needs a total of 3.2 kilograms of mud for his garden. He has a pile with 38 grams, a pile with 1.07 kilograms, a pile with 1.323 grams, and a pile with 0.971 kilograms. Does he have enough mud for his garden? So this was a non-calculator question. So if we put this in terms of grams, it's entirely up to you. You can do it as grams or kilograms. We've got now, he needs 3.2 kilograms. There are 1,000 grams in a kilogram, so there are 3,200 grams that he needs. If we look at what he's got 38, that's his first one. He's got 1.07 kilograms. This is going to be 1,070 grams. We got 1323, so 1323 grams. And we got 0.971 kilograms, which is 971 grams. So let's go ahead and add this up. That's going to give me 8, 11, 12, so 2 and carry the 1. 10, 12, that's going to give me 12, 19, 20, so that will give me 2. We've got on here now, that's going to be 3 and 9, which is 12, so that's going to give me now 14, and that goes there, so that's 3. So yes, he does by 202 grams. So all we've done is looked at converting the units. Some of those look quite tricky, but it would be a non-calculator question. So just get used to your metric conversions. Right, let's now look at speed, distance, time. If you can remember this triangle, it's going to help you out. You certainly don't need to. You might just have them learnt in your head. What we've got down the bottom is S. S is for speed, D is for distance, and T is for time. All we do, if we want one of these, let's say we wanted now the speed, we would put our finger over speed, cover speed, and we can say that speed is distance divided by time. This is a divide bar and this is multiplication. So speed is distance divided by time. If I wanted distance, we can say this is speed multiplied by time, or speed times by time. If we wanted time, put your finger over time, and it's distance divided by speed. So that's what we get. So let's look at some basic questions and then we'll look at some more challenging ones. It says a car travels for 3 hours at 50 miles an hour. We need to find the distance. So all I'm going to do here is just grab this up and we'll just have a circle. So if I have the circle, and we'll just change its colour. So if we fill it in now as well. So on this particular case, on the first question, we want the distance. So all we do is put the distance and we put our finger over distance. So the distance now is simply speed times by time. So what we've got is 50 miles an hour times by 3 hours. So all we're going to have in total here is 150 miles. So we've done 3 hours at 50 miles an hour, and that gives us 150 miles. If we look at the next one, a lorry travels 100 miles in 4 hours. Find its average speed. So we want the speed, the average speed. We put our finger over speed and we simply work it out. So the speed now is going to be the distance, which is going to be 100, over the time, which is going to be 4. If you want to put miles here and you want to put hours here, 100 divided by 4 is 25, and then this is miles per hour. So we can write MPH. It's miles over hours. Next one, find the time it takes a motorbike to travel 30 kilometres if it's travelling at 60 kilometres an hour. So this time we want the time, so I just put my finger over time, and we do the distance divided by the speed. So here we've got the distance, which is going to be 30. So this is 30 kilometres divided by the speed, which is going to be 60 kilometres per hour. So 60 kbh. 30 over 60 is going to be 1/2. So this is going to be now 1/2 of an hour. Don't panic on that. That's what you'd expect. If he's doing 60 kilometres in an hour, or she's doing 60 kilometres in an hour, 30 kilometres will take half an hour. Right, we need to be very careful in some cases when we're using fractions for an hour. So let's just look at some of these. We'll quickly run through these. Write 15 minutes as a fraction of 1 hour. Well, it's 15 of 60, which simplifies to 1/4. In your calculator, you can do that, and you can simply do 15 divided by 60. So 15 divided by 60 gives us 1/4. It's 1/4 of an hour. So let's look at this now and how we're going to use this, because this is one of the areas that students make a lot of errors on. A car travels at 60 miles an hour for 2 hours and 15 minutes. How far does it travel? So if we look at this, what we want is the distance. So the distance is the speed multiplied by the time. So we can say now that the distance, how far it travels, is going to be the speed. The speed is 60 multiplied by the time. And this is where students go wrong. They do this. They put 2 hours and 15 minutes. That is not correct. It's 2¼ hours. So we can put 2¼ hours or 2.25 hours. Make sure you're comfortable with that. So all you do is simply go ahead. What's that going to be? 135. So 60 times by 2.25 or 2¼ and that's 135 miles. Do make sure you've got this right. Let's do the next one. A lorry travels 12 miles in 20 minutes. What is its average speed? So we want speed, so we know that speed is going to be distance divided by time. So if we write this down, let's put here speed. So speed is going to be distance. The distance is 12 divided by the time. So here we've got 20 minutes. If we consider 20 as a fraction of 60, this is going to give us 1/3. 20 in 60 goes 3 times, so we do 12 divided by 1/3. 12 divided by 1/3, 12 divided by 1/3 is the same as doing 12 times by 3, which is going to be 36, and that will be miles per hour, and we need the correct units on. So make sure you're comfortable with those particular conversions. Okay, let's look at the next one. It says a car travels, I think that's travels 60 miles at an average speed of 80 miles an hour. How many minutes did the journey take? So what we want is the time. The time is going to be the distance divided by the speed. So if we look at this now, we'll write this here. The time is going to be now the distance divided by the speed. 60 divided by 80. In a calculator, this will give you 3/4. So if we do 60 divided by 80, this will give us 0.75 or 3/4. That is 3/4 of an hour. On this, if you type or hit that one, this will give you hours, minutes and seconds. So this button here will convert that to give us 45 minutes. So for example, if I had 1.2 hours, this would give me now 1 hour, 12 minutes and 0 seconds. If I had 1.5 hours, let's put this on, this would give me now 1 hour, 30 minutes. So do use that button. So there we go. That is now looking at speed, distance, time. Right. Let's now look at distance time graphs. So this is an example of a distance time graph. So what we have then is now on here, the distance from a fixed point and the time taken. So it says the diagram above shows the distance time graph for Sue's day out. The vertical axis shows the distance she is from home. Horizontal axis shows the number of hours that have passed since she left. Major thing to look at with a distance time graph is the gradient of a line. So the gradient of the line gives us the speed. So if we just look at this now, we can see different speeds are going on, and also we've got this straight line, this horizontal line just here, and that tells us that we weren't moving at all. So if we've got a horizontal line, there is no speed as it's stationary. So it says, use the graph to answer the following questions. What was she doing between 1 and 3 hours? Well, let's just talk our way through this graph. She starts at home, and that's a distance of 0 from home. 1 hour later, she's 4 kilometres from home. She doesn't move any further away from home for 2 hours. She then starts moving away from home again, and she moves 2 kilometres in 3 hours. She then moves back towards home for 2 hours. Then she stays stationary again, and then she returns home. If the graph had ended here, she would have finished 2 kilometres away from home. So what was she doing between 1 and 3 hours? We can say she was stationary or at rest. In the next part, it says, how far did she travel in the first 3 hours? Well, we can see that she travelled 4 kilometres here and no more kilometres there. So in the first 3 hours, she travelled a total distance of 4 kilometres. How far did she travel altogether? So if we look here, we've got 4 kilometres, no kilometres, 2 kilometres. That gives me 6 kilometres. She then travels another 4 kilometres and then she travels another 2 kilometres, so that's 12 kilometres in total. The next one, how long did she spend resting? We're looking for these horizontal lines. 2 hours plus 2 hours is going to give us 4 hours. What was the maximum distance she was away from her home? Well, that's going to be 6 kilometres. It's the top of this particular point here. What fraction of the total time was spent moving? If we look, we can see that she was at rest for 4/11ths of the time. So this was rest. So she must have been moving 7/11ths of the time. So we can see that 1, we've got 4, we've got 6, we've got 7 hours when she was moving. So what fraction of the total time was spent moving? 7/11ths. What was her average speed in the last hour? So if we look now, this is the gradient of a line, or the change in y over the change in x, or if you like, the rise over the run. So this distance is 2 kilometres and this is 1 hour. So all we have to do is 2 kilometres in 1 hour, and that's 2 kilometres per hour, 2 kph, or you can say 2 kilometres an hour, like so. So that's what we've got. What was her average speed overall? And it says excluding the stops. So what we've got her travelling now for 7 hours in total, and she's travelled 12 kilometres. So total distance travelled is 12, the moving was 7, so what we want is the speed. The speed is the distance divided by the time, so it's 12 over 7, and that is going to be kilometres an hour, or kph. And you could write that as a decimal answer, perfectly fine. Which section was she travelling the slowest on, and how can you tell? The slowest section is the one with the least gradient. Here we can see that the gradient is going to be 4. Here we can see that the gradient is going to be 2 over 3. Here we can see the gradient, although it will be negative, is going to be 4 over 2. And here the gradient is going to be on here 2 over 1. So we can say that it's this section here, that is where she was travelling slowest, because the gradient was the least steep, or the flattest gradient. So that gives us now the distance time graphs. You might be given something on velocity time graphs or real life graphs. I'll quickly go over this to give you some idea. So this is a velocity time graph. We get the time in seconds and the velocity or speed. So on this, we can have the acceleration from the gradient, if you're asked about the acceleration. So the acceleration here was going to be, we've got 4 meters per second over 2 seconds. So the acceleration will be 2 meters per second squared. We can also use one of these particular graphs to find the total distance travelled by finding the area under the curve or the graph. So if it's a selection of straight lines, then we can just go ahead and find the area. If it's a curve, we can estimate it. So if we looked now at the area under here, we can see that this top is going to be 3. We can see the bottom is going to be 9, and we can see the height is going to be 4. So using the area of the trapezium, we do 9 plus the 3, or 3 plus the 9, divided by 2, and we multiply that by the height. So that's going to give me 6, so that's 6 times by 4. 6 times by 4 is going to be 24, and it will be meters. You could, of course, split this into rectangles and triangles. I'm kind of skipping over this a little because I appreciate that it might not come up. But certainly if it does, the questions will be relatively basic. Okay, let's look at moving on. We're now going to move on and look at two different compound measures. In terms of the depth that these are covered in, it's not going to be massively great in this particular unit. They both come down from a higher tier. And the first one we'll look at is density, mass and volume. Again, you're not given the formula for this, but if you have a triangle, it's quite easy to work them out. So what we'll have is the following, and we will have D at the bottom for density. So density, then we'll have mass, and then we'll have volume. So it works like the speed, distance, time triangle. So let's look at some questions. It says a block has a mass of 300 grams and a volume of 10 centimeters cubed. We need to find the density of the block, given our answer in grams per centimeter cube. The nicest way to think about density is that density is mass divided by the volume. So something such as a snooker ball will have high density, yet something like a polystyrene ball of the same size will have a low density, because we've got now a much greater mass over the same volume for a snooker ball than we have a polystyrene ball. So let's go ahead and use this. In fact, I'm just going to steal my thing that we had before, this, so we can use this. Let's just copy that. We'll take that with us. I probably could have done it quicker by just doing a new one, but we'll go from there. So let's get to, there we go. So if we do that now, so let's look at the first one. So a block has mass 300 grams and a volume of 10 centimeters cubed. We need to find the density, and so we put our finger over density. So all we do is simply now do the mass divided by the volume. So we can say now that the density will be equal to the mass. Well, we've got a mass now of 300, and we're going to divide that now by the volume, which is going to be 10. So we can say the density is simply going to be 30, and that is grams per centimetre cubed. So nice and straightforward, it's all we need to do. On the next one, it says a block has density 8.4 grams per centimetre cubed and volume of 50 centimetres cubed. We need to find the mass. So the mass is the density times by the volume. So if we go ahead, we can simply write out now the mass is going to be equal to the density. So the density is going to be on here. This is 8.4. And what we've got here is grams per centimetre cubed. If I wrote grams per centimetre cubed, that's what it looks like. It's grams over centimetres cubed. And we multiply this by 50. And if I put the centimetres cubed here, when we multiply it, these will cancel off. So all we've got is essentially 50 times by the 8.4. Again, if you want to do it on a calculator, 8.4 times by 50, and we will give our answer now in grams. So that's going to give us now 420. So the mass is going to be 420 grams. So if I just clear those or cancel them off, you can see. So on the next one, it says a block has density 12 grams per centimetre cubed and mass 240.3 grams. We need to find the volume of the block. So all we need to do is the mass divided by the density. So let's go ahead and do that. So if we do that, we want now the volume. So V is going to be equal to the mass. The mass is going to be 240 grams. So let's just put that 240.3 G. And then we've got now this one, which is going to be, and I'm just going to write this slightly different, 12G over centimetres cubed. So what we end up here with, if we just do this, so what's that going to give me? 240.3 divided by 12. That's going to give me, we need divided, not times. Let's put that in, divide by 12. So what do we get? 20.025. So this is going to be 20.025. And we should hopefully know that this is going to be in centimetres cubed. It's a volume. Another way of thinking about it, those will cancel. If we're dividing 1 by 1 over centimetres cubed, that will then be multiplying by centimetres cubed. But hopefully you can just spot the units anyway. So that one is density, mass, volume. The other one is pressure. This is quite straightforward. Pressure. If you have, let's say you've got a cuboid now, and the cuboid looks something like so. So in fact, let's just do this and make a cuboid. Depending on which way round, let's say there was some force through this, so force from the weight of this particular cuboid. We'll group all of this together. And what we could do is the following. Let's just group. That's what we want to do. Group it. So let's say now there was a force acting downwards, and let's say this was going to be 10 newtons. If we've got 10 newtons, and that's what we measure force in, if I had the block on this particular end, the pressure would be greater because the area in contact with the floor is going to be less. If I flipped it over on its side, the pressure would be less because there's a greater area on the floor. So the smaller the area you have, the more pressure we have. It's often if you're on a chair and you swing back on two legs, you've got more force going through only two legs on the floor rather than four legs on the floor. Or if you think about a stiletto heel, if you put your foot down and you've got both the heel and the front part on the floor, the pressure is going to be a lot less than if you try and stand on the heel alone, which is highly likely to break. So all we do to work this out is, I don't think you'll be asked in terms of explaining it an awful lot well, but you do need to be comfortable with the triangle again to work out certain things. So we have P, F and A. So we can see on here that the pressure is the force divided by the area, the force is the pressure times the area, and the area is the force divided by the pressure. So if we still got our circle, hopefully, I know that's we've already done something different, haven't we? So if I go ahead and just copy that again, we will do a few questions. So let's have a look at the first one. It says a force of 30 newtons is applied to an area of 5 meters squared. We need to calculate the pressure in newtons per meter squared. So they've been nice and given us what we want. So all we need to do is the force divided by the area. So we're going to say now that the pressure is going to be the force. The force is 30 newtons divided by the area of 5. So that's going to give us 6. And that will be newtons per meter squared. And you can probably see why it's going to be newtons per meter squared, as we're dividing newtons, 30 newtons by 5 meters squared. It says the pressure between the floor and a box with a base of 3 square meters is 16 newtons per meter squared. We need to find the force exerted on the floor. So if we want the force, we just put a finger over force. So we can say now that the force is going to be equal to, we've got now the pressure multiplied by the area. So the pressure is going to be 16 newtons per meter squared, and we multiply that now by 3 square meters, and this is going to give us 48 newtons. Again, if you look at that, what you're multiplying by, you're multiplying 16 newtons per meter squared by 3 meters squared. So they're going to cancel off to give you 48 newtons. If we look at the last one, it says a boy stands on one leg on a half floor. The boy has a weight of 500 newtons. The pressure between the floor and his foot is 35,000 newtons per meter squared. Find the area of the bottom of this foot. So what we need to do is the force. So let's get the area. The area is going to be the force. So the force, what have we got as the force, and we're told this, haven't we? Force is 500 newtons, and we need to divide this by 35,000 newtons, and that will give us now the area in meters squared. So as you'd expect, this is going to be quite low. So let's just cancel those. So what's that going to be? That's going to be 1 over 70, 1/70th. So the area is going to be equal to 5 into 350, that's 1 over 70, and that's going to be meters squared. Let's just check that, such I'm not going mad because I've been going 4 hours now, and We're not a million miles off finishing, so hopefully this will get there quickly. So that's, yeah, 1/70th of a metre squared. Okay, let's now quickly look at the kinematic equations, or the constant acceleration equations. You may get questions on these, but if you are given them, you will be given the formulae. So what we have are the formulae, and I'll write these down and show exactly what each one is. We'll do a couple of these. As stated, I don't think they will be incredibly challenging at this level. What we have are what we call the SUVAT equations, SUVAT. This is the displacement. So displacement is almost like a distance, but we can go either in a positive or negative direction. This is what we call the initial velocity. So this is the start speed, but velocity has a direction as well. V is the final velocity. So final velocity. We've got A is the acceleration. So acceleration. And T is the time. So we are given now these three formulas. V is equal to U plus AT. So the final velocity is equal to the initial velocity plus the acceleration times time. The displacement S is equal to U multiplied by T plus 1/2 AT squared. So that's saying the displacement is equal to the initial velocity times by time plus 1/2 lots of the acceleration time squared. And finally, we would be given V squared is equal to U squared plus 2AS. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. But as stated, you will simply have to substitute into these from here. Okay, let's just do a couple of them. As I say, I think they're going to be relatively straightforward if you do get them. A car starts from rest and passes a point X with velocity 24 meters per second. After 15 seconds of travel, we're asked to find the acceleration of the car. So let's read that again. A car starts from rest and passes through the point X with velocity 24 meters per second after 15 seconds of travel. We need to find the acceleration. So if we look what we have in the SUVAT, SUVAT, we want to find now the acceleration. That is this one. It starts from rest, so the initial velocity is 0. The final velocity is 24 meters per second, and this was after 15 seconds. So all we're going to do is pick one of these that we can use. So if we look what we have on here now U, we've got V, we've got T, and we want A. So all we're going to do is use this one just here and substitute the numbers in. So if we look at this, I'll substitute the numbers in. We're going to use V is equal to U plus AT. So we've got 24 is equal to 0 plus 15 times by A. So 24 is equal to 15A. So all we need to do is simply divide 24 by 15. So 24 by 15 is equal to the acceleration. You could give this as a mixed number or a decimal answer, and that will be meters per second squared. So what's that going to give us? 24 divided by 15. 24 divided by 15 is going to give us now 1.6, and that will be meters per second squared. I think I will leave it at that one. I really think if you are asked to do this, it will be quite challenging, but hopefully it's just a case. I think it will be more structured than this. They will say use this equation to find these values given this. So those are the kinematics or constant acceleration equations. Okay, let's now quickly look at vectors. Vectors are directed line segments. So if we look here, what we have are some vectors, and I'm going to write these on. We use the notation the vector AB. The vector AB, we have now AB and an arrow above it. all we do is simply write, like we saw before on the translations, a vector. So with this one, we've gone from A to B. From A to B, we go right by 2 and up by 1. So the vector AB is going to be 2, 1. If we look at the vector CD, I want to go from C to D, I need to go left 1 and down by 3. So this is going to be -1, -3. If we look at the vector DC, we don't have to work this out. We can simply say now that it's going to be +1, +3. The vector DC is -CD. The vector BA is -AB. You're just going in the opposite direction. So if we look at the vector EF is going to go across by 2, and that's to the right. It doesn't increase on the negative or positive, so this will be 2, 0. The vector F to E would be -2, 0. So if we had to find F to E, that's going to be -2, 0. If we look now at the vector GH, so the vector G to H, well, with this one, we've gone across to the right by 4 and up by 2, so this will be +4, +2. If we wanted the vector H to G, we would simply now do the opposite, left 4 and down 2. If we look at the vector I to J, this is going to give us now, we're left by 3 and up by 3, -3, 3. So these are vectors. So you might be asked to write down the vectors. With vectors, we can add vectors, subtract vectors, and multiply. So on here, we're asked to calculate each of the following. So what we've got is 2 plus 3 and 1 plus 2. We add the x's and we add the y's. So 2 plus 3 is going to give us 5. 1 plus 2 is going to give us 3. If we look at the next ones, we're adding these. 0 plus 2 is 2. -4 plus 1 is -3. Let's just look at what this means. What we'll have is the following. If I started here and I did 2, 1, 2, 1 will take me to there. If I now did 3, 2, 3, 2 is going to take me to there. What we can do is look at something that we call the resultant vector. When we add two vectors, the resultant will give me this just here. And as you can see here, what we've got is now this line, and that line here has gone 5, 3. So by adding those vectors, we've simply found the resultant one. So if we go 2 to the right and 1 up, followed by 3 to the right and 2 up, we've done 5, 3 overall. Let's now look at subtracting. We can go ahead and we can subtract from here. So if we look at the subtraction, we've got now, this is going to be 4 minus 2, which is 2, 5 minus 1, which is going to give us 4. This one, we've got -2 subtract -6, which will give us 4. 4 subtract 2, that's going to give us 2. On this one, we're adding, so that's going to give me -3, and that's going to give me 1. On this one, we're going to have now, so these will just be decimals. This is going to be 1.2 subtract 0.8, which is 0.4. Then we need to add this one, so that's going to be 8.4. On these ones, what we have is a scalar multiple. So what this is saying is 3 lots of -2, 4. If I drew -2, 4, and I'll try and put it just here, -2, 4 is going to look something like this. If we had something that was 3 times longer than that, what we would have is -6. So if we do this, what we'd have is -6, 12. We're simply multiplying. What that would tell me is that I would have a line that is parallel to this one, but it is going to be now on here 3 times longer. So these are what we call parallel vectors. So let's do that. Let's see if I can actually. I think I'm going to struggle making this 3 times longer. Perhaps I should have picked some easier ones to do. So that's what we have. Let's just put this back. Let's say I think I could probably get now one that's going to be twice as long. I can probably just put that on there. If we had one twice as long, which would end up somewhere down here, what we would have is a scalar multiple, what we call a scalar multiple, and that would be 2. So it's twice as long, but in the same direction. So they're parallel. And then finally on this one, what we've got is now 5 lots of 2, 0. So that's going to be 10, 0. So that's basic work with vectors. If we've got now a multiple of the other, then we can go ahead and just draw a line. It is going to be some multiple of that. So it'll be longer or shorter. So let's now move on, and we're going to start looking at right angle triangles and trigonometry. The first thing we're going to look at doing is finding a missing length in a right angle triangle. We're going to look at using Pythagoras' theorem. If we have 2 given sides, we can find a missing length in a right angle triangle using Pythagoras' theorem. So what I'm going to do is just go ahead and put on 3 triangles. Pythagoras' theorem says that if we have now 2 shorter sides, which we can call A and B, and a longer side, which we call C, we can say that A squared plus B squared is equal to C squared. If we sum, so we add the squares of the 2 shorter sides, it's equal to the square of the longer side. We call that longer side the hypotenuse. The hypotenuse is always opposite now the right angle. So let's say I had, for example, this length right here, and we said that this length was going to be 5 and this length was going to be 12, and we wanted to find this length here. We could call that length x. All we would simply do, and I'll just scribble it here, we could say now that 5 squared plus 12 squared is equal to x squared. So if we want to work this out, we can do now 25 plus 144 is equal to x squared. So 169 is equal to x squared. And we take the square root, the positive square root, as it's a length. The square root of 169 is 13. So x would be 13. Let's say we have now a different scenario, and that is where we are given the hypotenuse and we want to find a shorter side. So let's say we were given now this side and this length. We would say that this was, let's say that's going to be 25. Let's say this length is going to be y and this length is going to be 7. What we would do in this particular case is say now that y squared plus 7 squared is equal to 25 squared. So solving this equation, we would subtract 7 squared from both sides. So it would be 25 squared minus 7 squared. So if you're finding the hypotenuse, the longer side, you add. If you're finding a shorter side, you subtract. So what we get then is the following. We have y squared, 25 squared is 625. Our 7 squared is 49. So if I take that away, y squared is equal to 576. So y is equal to the square root of 576. Square root of 576 should give us 24. So that's going to give us that y is equal to 24. So y is 24. So let's put that there. So a squared plus b squared is equal to c squared. So let's go ahead, and it says on here, using Pythagoras' theorem, find the value of x and y in the triangles below. So here we've got the 2 shorter sides and we want the hypotenuse. So we have 3 squared plus 4 squared is equal to x squared. This gives us 9 plus 16 is equal to x squared. 25 is equal to x squared. So x is going to be the square root of 25 and x will give us 5. So this is going to give us 5. A common error is that students put that this is just going to be 25. You can't have a triangle that has 3, 4, 25. It simply would not work. We call this a triple, one of our Pythagorean triples. I don't think you'll need to know that, but I think it's interesting nonetheless. So on the next one, we've got this one. So this time we're given the hypotenuse. We've got the longer side and we want a shorter side. So we say y squared plus 8 squared is equal to 10 squared. So y squared is equal to 10 squared minus 8 squared. Y squared is equal to 100 minus 64. Y squared will be equal to 36. Taking the square root of both sides, y will be equal to 6. These won't always be integer values. I'm just doing nice examples to show you how to do it. So on this one, we need to find the value of x in the triangle below. So we need the longer side. So we say 4 squared plus 6 squared is equal to x squared. 16 plus 36 is equal to x squared. 52 is equal to x squared. So we're going to have the square root, and it's the positive square root because it's a length. We can't have a negative length. The square root of 52. The square root of 52 is about 7.21. So 7.21, and that's correct to 2 decimal places. So that is Pythagoras' theorem. All you do is a squared plus b squared is equal to c squared. You might get a question in context. Don't panic, just draw a triangle. It says show that the length of each diagonal in the rectangle below is 15.8 centimetres, correct to 1 decimal place. So the diagonal is just going to be this line here. So what we've got is a triangle, and I'm just going to draw the triangle. With the triangle, what we're going to have is something that looks like this. So we're going to have 9 and we're going to have 13. So what we want is this length just here. So we can say 9 squared plus 13 squared is equal to x squared. So this is going to be 81 plus 169 is equal to x squared. So that's going to give me now 250 is equal to x squared. So all we need to do now is take the square root of 250 and that will give us x. We have the positive square root. So the square root of 250 and that gives now 15.8. So 15.811 ... is x, and therefore we've shown it. So when we're trying to find a missing length in a right angle triangle and we've got 2 of the known sides, we use Pythagoras' theorem. If we don't have the 2 known sides and we have one angle and one side, we can use what we call the trigonometric ratios. So let's look at these and we will do a few examples of this. So what I'm going to do is the following. I'm going to put now on a right angle triangle this angle just here, and I'll say that this angle is going to be theta. We could have x or theta. We're going to label up this triangle here. Relative to now the right angle, the longer side is always the hypotenuse. The angle, if the angle's just here, the side opposite is called the opposite. And the one next to the angle is called the adjacent. What we have are 3 trigonometric ratios. We have sine, cosine, and tangent. So what I'm going to do is just put these here, and we're going to have, like we've done before, 3 triangles. So if we go ahead and do this, let's put this here and let's put this here. What we've got is the following. We can look at what we call the ratio on these, and we will have 3 different ones. So if we start off with the following ratio, we can say that the sine of the angle is the opposite over the hypotenuse. So in here I put SOH. The sine of the angle is the opposite over the hypotenuse. If we now look at the cosine, we can say that the cosine of the angle is the adjacent over the hypotenuse. So in our triangle, we can put this in. We know this is a divide line, or we could put cos theta is equal to the adjacent over the hypotenuse. The last one we're going to look at is the opposite over the adjacent, and that gives us tan, or tan theta. This is the opposite over the adjacent. You won't be given these, so you must remember them. Often people remember these using a mnemonic. This one, some old hags can't always hide their old age. There are plenty more. That's just one I remember from some time ago. So how can we use this? What we can do is use these to find the missing lengths in right angle triangles and missing angles. So let's start off by finding a missing length. What we'll do is have this angle just here, and I'm going to say that this is going to be 30 degrees. I'm going to put the right angle here, and we're going to find now the length just here, which I'm going to call X, and we're going to have now this length, which is going to be 10 centimeters. All we do is look to identify which values we've got relative to this angle. So if I look now at my triangle, I know that this is the opposite, which I want to find, and this is the hypotenuse, which I'm given. If we look at the three triangles, the only one that O and H appears in is the sine. If I had A and H, it would be cosine. If I had O and A, it would be tan. So what we want to do is find now the value, and I'll get my little, let's get this back up. This could be quite helpful. So if we do that, let's put this on here and we'll make it exactly how we had it before. If I want to find now the opposite, what I do is put my finger over the opposite and I simply multiply the sine of the angle by the hypotenuse. So what we can say on here is the following. X will be equal to 10 times by, or we can just write sine, 10 sine of 30 degrees. On the calculator, make sure you're in degrees mode. Shift mode 3. So all we have to do on here now is type in 10 times sine 30. Sine is just here and 30 is just there. That gives me that X is equal to 5. So X is equal to 5 centimeters. Okay, let's do another one. So let's say we've got this scenario and I've got now on here the right angle. I want to find now this length, which I'll call Y. I'm going to say that this is going to be 6 meters and this is going to be 40 degrees. So here is my triangle. If I look relative to this angle, this is the adjacent and this is the hypotenuse. The hypotenuse will always remain the same. So this would be the opposite, this is the adjacent. The only one of the three triangles that has that in is this one just here, the adjacent and the hypotenuse. I want the adjacent, so I put my finger over the adjacent, and we can say from this now that Y will be equal to the hypotenuse times the cosine of the angle. So this will simply be 6, and then we'll have cosine of 40 degrees. And we can type this straight into a calculator. 6 cos of 40. And that's going to give 4.596. So we can say 4.6. So that's going to be equal to 4.6 meters, correct to 1 decimal place. Let's say we had another one, and we'll put another one just here. This time, let's do the tan one. So let's say we've got now the right angle here, we've got 6 here, we've got 7 here, let's find a length first. Let's put here that this is going to be, let's put P, and let's put that this angle is going to be 35 degrees. So if we look what we've got relative to the angle, and I'll pop these on, we've got now the opposite. This is opposite the angle and this is the adjacent. All we want to do now is find the value of the adjacent. The only triangle that has O and A in is this one just here. So if we want to find the adjacent, I put this over the adjacent. So this time what we have is the value of P will be equal to the opposite, which is 6, divided by tan of 35 degrees. So this time, because I want the adjacent, is opposite over the tan. If I wanted the hypotenuse, it would be the adjacent over the cosine if we had the adjacent. If I wanted the hypotenuse given the opposite, it would be opposite over the sine of the angle. So let's go ahead and do that one. So this is going to be 6 over tan of 35 degrees. So that's going to give me 8.568 and so on. So we'll say this is going to be 8.6 and that's going to be correct to 1 decimal place. So that is how we find missing lengths. We need one angle and a length. We'll quickly look at finding a missing angle. When we're finding a missing angle, let's say this angle is going to be theta, and we want to now find this, we would need to be given two sides. So let's say we were given that this one is going to be 10 and this one is going to be 7. Relative to the angle, what we would have is the hypotenuse and we would have the adjacent. So if we look now, the only one that has the hypotenuse and the adjacent in is this one here. I want to get the cos of the angle first. So what I can write is that cos theta will be equal to the adjacent divided by the hypotenuse, 7 over 10. What we now need to do is find the angle. So we say that theta is equal to the inverse cos. This is cos to the -1, or on your calculator, shift cos. So shift cos of 7/10. Shift cos of 7/10 will give us that angle, and that will give us 45.6. That's 45.6, and that's to 1 decimal place. So if we had, quickly we'll do this one, let's say we had this angle x, and we had 9, and we had, for example, 13. This is the opposite, this is the hypotenuse. So we would simply say now on here, we want the sine of x. So the sine of x will be equal to 9 over 13. So x will be equal to the inverse sine of 9 over 13. And we can find that on the calculator. So shift sine, and then we've got 9 divided by 13, which you can put in like that, and it will give you 43.8 degrees. So those are using the trigonometric ratios, SO, CAR-TOA, or the sine, the cosine, and the tan. Let's just finish off. This is the last thing we're going to look at. And I do struggle sometimes to understand why certain things are on Foundation, and this is going to be one of them. What you'll need to learn are the sine, the cosine, and the tan values for 0, 30, 45, and 60, and know the values of sine and cosine of 90 degrees. I'm going to do a little bit on this, but appreciate that we're running a bit low. Well, we're spending a lot of time doing this. What I'm going to do here is draw now an equilateral triangle. In this equilateral triangle, I'm going to cut it in half. If I cut an equilateral triangle in half, what I'll have is an angle just here, and that angle is going to be 60 degrees here. So that one will be 60 degrees. This one is going to be 30 degrees, and the right angle is going to be just here. If each side length was 2, this would be 2, this would be half, and using Pythagoras' theorem, we can say now that this one is going to be, now if we just call this x, we would say now that x squared plus 1 squared is equal to 2 squared. So x squared will be equal to 2 squared, which is going to be 4 minus 1 squared, which is 1. So x squared would be equal to 3, and x would be equal to root 3. So this right here is going to be root 3. So if we look now at these angles, and again, this is quite abstract, and we look now at 30 degrees. If I write down now the sine of 30 degrees, well, that's going to be the opposite over the hypotenuse, which is going to give me 1/2. If I look at the cos of 30 degrees, the cos is going to be the adjacent over the hypotenuse. So relative to this angle, this is the adjacent and this is the hypotenuse, and that will give me root 3 over 2. If I now look at the 60 degree angle, in fact, let's do tan, let's not forget tan. So if we do tan 30 is going to be now the opposite over the adjacent. So this is 1 over root 3, and that gives us that value there. If we now look at the sine of 60 degrees, we've got the 60 degrees here, so the opposite is root 3, and the hypotenuse is 2. Root 3 over 2. The cosine of 60 degrees is going to be now the adjacent over the hypotenuse, which is 1 over 2. If we now look at the tan of 60 degrees, the tan of 60 degrees is going to be the opposite over the adjacent, which is going to be root 3 over 1, which of course we could just write as root 3. So hopefully you can see all I've done here, if this is 30 degrees, this is the opposite, this is the adjacent, and this is the hypotenuse. If we've got now the 60, then this is the opposite, this is the adjacent, and this is the hypotenuse. So that is looking at those angles, and I'm only going to do a few, and if we do the next one. Let's say now on the next one, we have a square, and we cut this in half. If we cut this in half like so, we should hopefully recognise now that these are going to be 45 degree angles. So this is 45, and this is 45, and this is a right angle. So if this was my little triangle, and I said this side length was 1, this side length was 1, we can use Pythagoras' theorem to find this. So let's say that this is just y. Y squared will be equal to 1 squared plus 1 squared. So y squared will be equal to 1 plus 1. Y squared is equal to 2. So y is the positive square root of 2, and we say that this is root 2. So let's look now at the sine of 45 degrees. So if we take this now, our 45 degrees here, this is the opposite, and this is the hypotenuse. That is going to be 1 over root 2. If we do cos of 45 degrees, well, that is the adjacent over the hypotenuse, which again is going to give 1 over root 2. If we do the tan of 45 degrees, so tan of 45 degrees, that is going to be 1 over 1, which just gives us 1. So we've derived those. We can look at 90 degrees, the sine and the cosine of 90 degrees. I would just simply remember them as 0 and 1 for sine of 0 and 90, 1 and 0, and then tan is 0. Personally, I think it's easier to commit the table to memory. Certainly at this level, I think it's a real tough ask. So I've introduced it. I've not spent an awful lot of time on it. But there we go. So that brings us to the end of the geometry and measures chapter. So 4 hours, 37 minutes, and we're all done.